Hello there and welcome to Physics with William, where curiosity gets comfortable, difficult questions are given plenty of room, and science is allowed to take its time. Tonight we're going to look at something that seems completely familiar until we stop and ask what it really means. We're going to ask where matter gets its temperature from. That may sound like a simple question. A cup of tea is hot because the water was heated. An ice cube is cold because it came from the freezer. A radiator is warm because hot water is moving through it. A metal spoon left on the kitchen counter is usually somewhere in between. We know how these things feel, and we know how to change them. We can warm food in an oven, cool a drink with ice, rub our hands together on a cold day, or step into sunlight and feel our skin grow warmer. Yet none of those examples quite answers the deeper question. What is it inside matter that makes one object hot and another cold? Where is temperature located? Is it stored in the atoms like water in a tank? Does heat sit between the particles? Does every atom carry a tiny thermometer? And if all matter is made from particles, why do different materials at the same temperature feel so different when we touch them? Before we begin, where are you listening from tonight and what is the temperature like around you? Perhaps the room is cool and quiet. Perhaps there is a warm drink nearby. Maybe you're under a blanket near an open window or trying to find the one side of the pillow that still feels pleasantly cold. Wherever you are, your body is already exchanging energy with the matter around it. Even while you sit still, heat is moving through the air, through your clothing, through the chair or bed beneath you, and across the surface of your skin. If you find this kind of slow scientific journey soothing, you can like the video and subscribe to the channel. It helps this calm corner of physics reach other people who enjoy learning without being hurried. And as always, there is no test at the end, no need to remember every term, and no requirement to stay awake for all of it. The atoms will continue moving whether or not we are watching them. To understand temperature, it helps to begin with an ordinary scene. Imagine a mug of tea resting on a wooden table. The tea is hot. The mug is warm. The table feels cooler. The air in the room feels cooler still. If we leave the mug alone, the tea slowly cools. The mug cools with it. The nearby air warms by a tiny amount and some energy spreads into the table. After enough time, the tea, the mug, the table, and the surrounding air move toward the same temperature. Nothing mysterious seems to happen. There is no flash, no sound, and usually no dramatic announcement from the kettle. The tea simply stops being as hot as it was. But from the viewpoint of physics, an enormous amount of activity is taking place. The water molecules in the tea are moving, rotating, vibrating, and colliding. The atoms in the mug are vibrating in their positions. Molecules in the air strike the outside of the mug and carry energy away. Light, including invisible infrared radiation, leaves the warm surface and travels into the room. The table receives energy where it touches the mug. Every part of the process involves energy being shared, transferred, and redistributed. Temperature is connected to that microscopic activity. It is not a separate material added to an object. A saucepan does not become hot because it fills with a substance called heat. A block of ice does not become cold because coldness has been poured into it. Temperature describes the energetic state of the particles that make up matter. In the simplest everyday picture, hotter matter has particles with more energetic microscopic motion, while colder matter has particles with less. That sentence is useful, but it needs careful handling. The particles inside matter do not all move at one identical speed. In a gas, some molecules move quickly, some move more slowly, and collisions constantly change their directions and speeds. In a liquid, molecules remain close together but still move around one another. In a solid, atoms or molecules are held in an organized structure, yet they are not perfectly still. They vibrate around their usual positions. Temperature tells us something about the overall pattern of this motion and energy, rather than the exact behavior of one chosen particle. This is why asking for the temperature of a single atom can be awkward. Temperature is most useful when we're talking about a collection of particles. One atom may have a certain amount of energy and a certain motion, but temperature describes the statistical behaviour of many particles together. It is similar to asking about the average pace of a crowd. One person may be walking quickly, another may be standing still, and someone else may be moving in the wrong direction while looking for the exit. The crowd can still have an overall pattern. Even though every person is doing something slightly different, matter gets its temperature from the energy distributed among its microscopic parts. That energy can arrive in many ways. Sunlight can be absorbed by a surface. A flame can transfer energy to a pan. Electric current can move through a wire and increase the motion of atoms in the material. Friction can change organised motion into disorganised microscopic motion. Compression can warm a gas by forcing its particles into a smaller region where energy is redistributed through more frequent collisions. Chemical reactions can release stored energy. Nuclear reactions inside stars can produce energy that eventually reaches planets as radiation. Even a person sitting quietly produces heat through chemical processes taking place in cells. A warm object therefore carries a history, even if that history is not obvious. The warmth of a stone in the afternoon may have come from hours of sunlight. The warmth of a laptop may come from electrical energy being used by its components. The warmth of your hands may come from metabolism and blood flow. The warmth of soup may come from a cooker, which may have received energy from burning gas or from electricity generated many miles away. Temperature is the present condition, while heating describes one of the ways that condition can change. This distinction is important because temperature and heat are related, but they are not the same thing. In everyday conversation, we often use the words as though they mean the same thing. We say that an object contains heat, or that the heat outside is high. Physics is more particular. Temperature describes the thermal state of matter. Heat refers to energy transferred because of a temperature difference. When the hot tea warms the mug, energy is transferred from the hotter tea to the cooler mug. When the mug warms the air, energy is transferred again. Once everything reaches the same temperature, the net transfer settles down. The particles are still active, but there is no longer a temperature difference pushing energy mainly in one direction. Our senses can notice some of these transfers, but they do not measure temperature directly. Touch a wooden table and a metal spoon that have been sitting in the same room all night. They may have nearly the same temperature, yet the metal often feels colder. That is not because the metal has secretly ignored the room and chosen a colder lifestyle. It feels colder because metal transfers energy away from your skin more quickly than wood does. Your nerves respond strongly to the rate at which energy leaves or enters your skin. They are excellent at warning you about possible danger, but they are not laboratory thermometers. This also explains why cool water can feel warm after your hand has been in ice water, and the same water can feel cool after your hand has been in hot water. The water has one temperature, but your two hands can report different experiences. Each hand begins in a different thermal state, so energy moves between the water and the skin in different ways. The sensation depends on the direction and speed of the transfer, as well as the temperature of the nerves before contact. A thermometer gives us a more consistent method. Traditional thermometers rely on a material that changes predictably with temperature. A liquid may expand as it warms. A metal strip may bend because two metals expand by different amounts. Electronic thermometers use changes in electrical behaviour. Infrared thermometers detect radiation coming from a surface. None of these devices sees temperature as a glowing label attached to matter. Each one measures some physical effect that is closely connected to the microscopic energy of the material. For most of human history, people could feel warmth and cold without knowing about atoms. Fire cooked food, sunlight warmed the ground, and winter air chilled exposed skin. Temperature was experienced long before it was precisely measured. Early ideas often treated heat as a kind of invisible fluid that could flow from one body into another. This picture seemed reasonable because warmth does spread, and hot objects do cause nearby objects to become warmer. A hidden fluid appeared to explain what people observed. The problem was that friction could produce apparently endless amounts of heating. When two surfaces rubbed together, they grew warm. If heat were a fixed fluid stored inside matter, repeated rubbing should eventually use it up. Instead, mechanical work could keep producing more thermal energy as long as the motion continued. This helped scientists understand that heating was connected to energy and motion rather than to a special substance hidden in objects. You can demonstrate the same idea without an 18th century laboratory. Rub your palms together for several seconds. They become warmer. You have not created matter, and you have not released a pocket of trapped fire from your fingers. Muscles use chemical energy to move your hands. Friction resists that motion. The organized movement of your hands is partly transformed into less organized microscopic motion within the skin and nearby air. The temperature rises because energy has been redistributed into the small-scale movements of matter. The word disorganized can be misleading if it sounds as though atoms are being careless. It simply means that microscopic motion points in many directions and is not coordinated into one visible movement. A rolling ball has organized motion because the ball as a whole moves across the floor. When friction slows it down, some of that organized energy becomes microscopic motion in the ball, the floor, and the surrounding air. The ball and floor become warmer by an amount that is often too small to notice. The visible movement fades, but the energy has not simply vanished. The reverse can also happen. Thermal energy can be turned into organized motion. In a steam engine, heating water produces high-pressure steam that can push a piston. In the atmosphere, uneven heating helps drive winds. Inside Earth, heat contributes to slow movement in the mantle. Temperature differences can make matter move on scales ranging from a pot of simmering soup to weather systems covering entire regions. Even so, temperature is not just a count of how much total energy an object has. A bathtub full of warm water can contain more thermal energy than a small cup of very hot coffee, even though the coffee has the higher temperature. The bathtub contains far more matter, so there are far more molecules sharing energy. Temperature describes the average microscopic condition, while total thermal energy also depends on how much matter is present and what kind of matter it is. The type of matter matters because particles can store energy in different forms. They can move from place to place, they can rotate, they can vibrate. Atoms within molecules can shift relative to one another. Electrons can occupy different energy states. In solids, collective vibrations can travel through the structure. At very high temperatures, electrons may separate from atoms, producing plasma. At very low temperatures, quantum behavior becomes increasingly important. The simple picture of faster particles meaning higher temperature remains a helpful starting point, but the full story includes several ways for microscopic systems to hold and exchange energy. This is one reason equal amounts of energy do not warm every substance by the same amount. Water requires a relatively large energy input to produce a given temperature rise. Many metals warm more quickly with the same energy input. A sandy beach may become hot during the day, while the nearby sea remains cooler, then the sand cools rapidly after sunset, while the water releases stored energy more slowly. The particles and bonds within each material provide different ways to absorb and distribute energy. Temperature also depends on balance. Place a hot object next to a cold object, and energy tends to spread from the hotter one to the colder one. This direction is so familiar that we rarely question it. A cold spoon placed in soup warms up. The soup cools slightly. We do not expect the spoon to become colder, while the soup becomes even hotter without some outside influence. At the microscopic level, particles collide and exchange energy in both directions, but the overall transfer favours a more even distribution. Eventually, the objects can reach thermal equilibrium. This means they share the same temperature and no longer exchange energy in a way that produces a net flow from one to the other. Their particles have not stopped. The soup is not frozen in place, and the spoon has not become microscopically silent. energy continues to move among particles, but the large-scale temperature difference has disappeared. The idea of equilibrium allows thermometers to work. When a thermometer is placed in contact with an object, energy passes between them until the thermometer reaches nearly the same temperature as the object. The reading then tells us the thermometer's own temperature, which we use as a practical measure of the object's temperature. A good thermometer is designed so that it reaches this balance predictably and does not significantly change the thing being measured. This becomes more interesting when we look beyond everyday temperatures. Deep space is not simply a place with no temperature. Thin gas between stars can be extremely hot in terms of particle energy, even though it would not heat you in the same way as dense air, because there are so few particles available to transfer energy. A cloud of gas may have particles moving at very high speeds, yet the total energy arriving at an object inside it can remain small. Temperature, density, and rate of energy transfer must be considered together. The same caution applies to cold. Cold is not a separate form of energy that flows into matter. When an object cools, it loses thermal energy to something else, or its energy becomes redistributed through a process that lowers its temperature. A freezer does not manufacture coldness and inject it into food. It uses work to move energy from inside the cooled space to the room outside. This is why the back of a refrigerator feels warm. The machine is taking energy from one place and releasing it in another, along with additional energy used to run the compressor. There is a lowest possible temperature, often called absolute zero, where a system has as little thermal energy as the laws of physics allow. It does not mean that every particle becomes a perfectly motionless marble. Quantum mechanics prevents such a completely still picture from being accurate. Reaching absolute zero exactly is not possible through a finite cooling process, though scientists can come extraordinarily close. Near that limit, matter can behave in ways that seem very different from ordinary solids, liquids, and gases. At the opposite extreme, matter can reach temperatures so high that atoms cannot remain intact. Electrons separate from nuclei, and the material becomes plasma. In stars, lightning, and certain laboratory experiments, temperature reflects violent microscopic energy. Yet even there, the same general question remains. How is energy distributed among the particles, and how does that distribution change through collisions, radiation, expansion, and other processes? Our own bodies stay within a narrow temperature range because biology carefully manages energy. Cells release energy through chemical reactions. Blood transports warmth. Sweat removes energy when it evaporates. Tiny muscles can contract rapidly during shivering, turning chemical energy into motion and then into thermal energy. Blood vessels widen or narrow to change how quickly energy reaches the skin. Feeling warm or cold is therefore not only about the room. It also depends on what the body is doing, how quickly energy is being produced, and how quickly it is being lost. A blanket does not create heat in the usual sense. It slows the transfer of energy from your body to the cooler surroundings. The air trapped within the blanket is a poor conductor, so the energy produced by metabolism remains near you for longer. This is why a blanket that feels useless when folded on a shelf becomes wonderfully effective once wrapped around a warm person. The person is the main energy source. The blanket is the patient assistant that keeps the energy from leaving too quickly. Sunlight works differently. Radiation travels from the sun across space and is absorbed by matter on Earth. When the light interacts with atoms and molecules, its energy can be converted into microscopic motion and other internal forms. A dark surface often absorbs more incoming visible radiation than a light surface, which is why it may warm more strongly in sunlight. The temperature rises when energy arrives faster than it leaves. Later, when the surface radiates and transfers energy away faster than it receives it, the temperature falls. This balance between incoming and outgoing energy determines the temperature of many systems. A planet receives radiation from its star and releases radiation into space. A house receives energy from heating, sunlight, people, and appliances, while losing energy through walls, windows, ventilation and radiation. A cup of tea gains energy from the kettle and then loses it to the room. In every case, temperature changes when the energy entering and leaving do not balance. At this point, the answer to our question is beginning to take shape. Matter gets its temperature from the microscopic energy of its particles and from the way that energy is distributed. Heating, cooling, friction, radiation, compression, expansion, chemical reactions, electrical processes, and nuclear reactions can all change that distribution. Temperature is not a hidden fluid or a label placed on an object. It is a large-scale description that emerges from countless small events. The interesting part is that those small events never stop. In the quietest room, air molecules cross the space and collide. In a solid wall, atoms vibrate. In a sleeping body, chemical reactions continue. In a cooling mug, energy moves into the table and air. The world that appears still at our scale is active at the microscopic scale. To see where temperature really begins, we need to reduce the scene. We can set aside the mug, the room, the thermometer, and even the sensation of warmth in the skin. We can look instead at the atoms and molecules themselves, not as fixed beads packed neatly together, but as a restless population that collides, vibrates, rotates, and shares energy in ways that create the familiar difference between hot and cold. At the scale of atoms and molecules, stillness is much harder to find than it appears. A book resting on a table looks completely motionless. A glass of water left beside it seems calm. The air in the room may feel quiet enough that nothing appears to be happening at all. Yet inside the book, the glass, the water, the table, and the air, particles are constantly moving. Their motion is usually too small and too rapid for our eyes to detect, but it is one of the main reasons matter has temperature. Begin with the air around you. Air is made mostly from molecules of nitrogen and oxygen, along with smaller amounts of other gases. These molecules are not arranged in fixed positions. They travel through the room in different directions, moving in straight paths for short distances before colliding with other molecules. Each collision changes their speed or direction. A molecule may move quickly toward a wall, bounce away, strike another molecule, and then continue along a completely different path. This movement does not create a noticeable breeze because the molecules are not all moving in the same direction. A breeze occurs when a large number of molecules develop an overall movement together. Thermal motion is less organized. Some molecules move left, others move right, and many move in every direction between. Their movements tend to cancel when viewed on the scale of the room, so the air as a whole may appear still even though its molecules are moving rapidly. When air is warmed, its molecules generally gain microscopic kinetic energy. Kinetic energy is the energy associated with motion. The molecules move faster on average, although they do not all move at one shared speed. Some are much faster than average, some are slower, and collisions continually change which molecules belong in each group. Temperature is connected to the overall distribution of these motions rather than to the speed of one particular molecule. Imagine looking at every air molecule in a room and recording how fast each one is moving. The result would not be a neat list in which every molecule has the same speed. It would be a broad spread. Many molecules would be moving at moderate speeds. A smaller number would be unusually slow, and another smaller number would be unusually fast. If the air were heated, that whole spread would shift. Faster molecular motion would become more common, but the differences between individual molecules would remain. This matters because a single fast molecule does not make an object hot. Even in cold matter, a few particles may carry much more energy than the average. In hot matter, some particles may temporarily move more slowly than expected. Temperature describes the collective condition of a large group. It is a statistical property, which means it becomes useful when many microscopic events are considered together. A gas gives us the clearest picture because its particles are free to travel over noticeable microscopic distances. In a liquid, the situation is more crowded. Water molecules in a glass are packed close together. They cannot usually move across the liquid without repeatedly interacting with neighbouring molecules. They slide, rotate, jostle and exchange energy while remaining close enough for attractive forces to hold the liquid together. This is why water keeps a definite volume but changes shape to match its container. The molecules are not locked into fixed locations, as they are in a solid, but they are not widely separated, as they are in a gas. Their motion allows them to rearrange, while their attraction prevents them from simply flying away under ordinary conditions. Heating liquid water increases the energy available to its molecules. Their movements and rotations become more energetic. Collisions become more vigorous. Some molecules near the surface may gain enough energy to escape into the air as water vapour. This is evaporation, and it can happen even when the water is well below its boiling temperature. The molecules that escape are often among the more energetic ones near the surface. When they leave, they carry energy with them. The average energy of the molecules left behind can decrease, which lowers the temperature of the remaining liquid. This is why evaporation produces cooling. Sweat uses the same process. Water on the skin absorbs energy, and some of the more energetic molecules leave as vapour. The energy they carry away helps cool the body. Boiling is a more widespread version of the change from liquid to gas. When water reaches its boiling point under a given pressure, bubbles of water vapour can form throughout the liquid rather than only at the surface. Energy supplied to the water helps molecules separate from one another and enter the gas phase. During this process, added energy does not always produce an immediate rise in temperature. Much of it is used to change how the molecules are arranged and how strongly they interact. This shows that microscopic energy is not limited to movement from one place to another. Molecules can also rotate. Their atoms can vibrate relative to one another. Energy can be stored in the forces between nearby molecules. When matter is heated, the added energy may be shared among several kinds of microscopic activity. A water molecule contains one oxygen atom and two hydrogen atoms. The molecule can move through space as a whole. It can rotate. Its chemical bonds can also flex and vibrate. Those different forms of motion do not all respond in exactly the same way at every temperature. Quantum mechanics controls which microscopic energy states are available, especially when the temperature is low or when a particular kind of vibration requires a relatively large amount of energy. For an everyday introduction, it is often enough to say that hotter matter contains faster moving particles. That statement is useful, but it is incomplete. In some materials, much of the added energy goes into vibrations or rotations. In others, it may change electronic states or the arrangement of particles. Temperature is related to how energy is distributed among all the microscopic possibilities that the material can access. Solids make this easier to overlook because their particles do not appear to travel around. In a solid piece of metal, atoms are arranged in a structured pattern. Each atom is held near a usual position by electrical forces involving neighbouring atoms and electrons. The atoms are not fixed with perfect rigidity, they vibrate around their positions. As the solid becomes warmer, these vibrations generally become more energetic. The atoms move farther from their average positions and change direction more rapidly. They remain part of the solid structure, but the structure becomes more active. If enough energy is added, the vibrations can become strong enough to disrupt the ordered arrangement, and the solid may melt. A solid is therefore not a collection of motionless atoms touching one another like neatly stacked marbles. The forces between atoms behave more like flexible connections, although this comparison should not be taken too literally. Push one atom slightly away from its usual position, and the forces from nearby atoms tend to pull or push it back. Its motion affects its neighbours, and their motion affects others. Vibrational energy can travel through the solid in coordinated patterns. Physicists describe these collective vibrations using a quantum idea called phonons. A phonon is not a tiny particle hidden between atoms in the ordinary sense. It is a useful way of describing a shared vibration moving through the atomic structure. This helps explain how thermal energy travels through a non-metallic solid. Vibrations in one region influence neighbouring atoms, passing energy through the material. In metals, mobile electrons also play an important role. They can move through the solid and transfer energy efficiently from one region to another. This is one reason metals often conduct heat much better than wood, plastic, or fabric. Place one end of a metal spoon in hot soup, and the handle gradually warms. Atoms near the hot end gain energy through interactions with the soup. Vibrations become stronger, and mobile electrons help carry energy through the metal. The energy spreads toward cooler regions of the spoon. The atoms do not have to travel from the soup to the handle. Energy can move through the structure while the material itself remains in place. Wood behaves differently. Its structure does not allow energy to move as quickly. It also contains small pockets of air, and air is a poor conductor when it is prevented from circulating freely. That is why a wooden spoon can remain comfortable to hold while part of it sits in hot food, whereas a metal spoon may deliver an unpleasant reminder that thermal conductivity is not merely a subject for textbooks. The restless motion inside matter also produces pressure. In a gas, molecules repeatedly strike the walls of their container. Each collision exerts a tiny force. The combined effect of an enormous number of collisions creates gas pressure. Heating the gas can make the molecules move faster on average. If the container cannot expand, the molecules strike the walls more frequently and more forcefully, so the pressure rises. If the container can expand, the gas may occupy more space instead. A balloon placed in a warm environment often grows slightly larger because the gas inside becomes more energetic and pushes outward more strongly. A balloon placed in a cold environment may shrink as the molecular motion becomes less energetic. The exact result also depends on the flexibility of the balloon and the pressure outside it, but the microscopic explanation begins with moving particles and collisions. Compression can work in the other direction. When a gas is squeezed into a smaller space, work is done on it. The moving boundary, perhaps a piston, collides with gas molecules and can increase their energy. The gas becomes warmer. This is why the barrel of a bicycle pump may heat up during use. Some heating also comes from friction, but compression of the air is an important part of the effect. Expansion can cool a gas because the gas may use its internal energy to push against its surroundings. As the gas expands, its particles can lose energy on average. This process is important in refrigerators, air conditioners, cloud formation, and the behavior of gases in the atmosphere. Matter can change temperature without touching something that is simply hotter or colder. Mechanical changes can alter the way microscopic energy is distributed. Collisions are central to this redistribution. When two particles collide, energy and momentum are exchanged. One particle may speed up while the other slows down. A rotating molecule may transfer some rotational energy into movement through space. Vibrational energy may be exchanged during interactions. Across countless collisions, energy moves through the population of particles. Given enough time and enough interaction, an isolated collection of particles tends toward thermal equilibrium. The energy does not become identical for every particle. Instead, it settles into a stable statistical distribution. Fast particles remain, slow particles remain, and constant exchanges continue. What becomes stable is the overall pattern. This is one reason equilibrium should not be confused with inactivity. A glass of water at room temperature may be in thermal equilibrium with the room, but its molecules are still moving. They continue to collide, rotate, and vibrate. Water molecules still leave the surface, and molecules from the air may return to it. Microscopic processes continue in both directions, while the average large-scale condition remains steady. The same idea applies when two objects reach the same temperature. Suppose a cool metal spoon is placed in warm water. At first, the water molecules near the spoon transfer more energy to the metal than the metal transfers back to the water. The spoon warms and the water cools slightly. As their temperatures approach one another, the net transfer decreases. Once equilibrium is reached, microscopic exchanges continue. but neither object experiences an overall gain of thermal energy from the other. This constant exchange is difficult to imagine because human senses smooth over microscopic detail. We see the spoon as one object and the water as another. We do not see individual collisions at the boundary, yet the boundary is extremely active. Water molecules strike atoms and electrons at the metal surface. Energy moves through electromagnetic interactions. The large-scale warming of the spoon is the accumulated result of an immense number of tiny events. Evidence for molecular motion appeared long before scientists could directly image atoms. One important clue came from the irregular movement of small particles suspended in water. Under a microscope, tiny grains such as pollen fragments can be seen wandering in unpredictable directions even when the water looks still. This is called Brownian motion. The visible grain is much larger than a water molecule. It moves because molecules strike it from all sides. At any particular instant, the collisions are not perfectly balanced. A few more or slightly stronger impacts may arrive from one direction, pushing the grain a short distance. A moment later, the imbalance changes, and the grain moves another way. The resulting path looks random because it reflects a huge number of unseen molecular collisions. Brownian motion helped establish that atoms and molecules were physically real rather than merely useful ideas. The visible wandering of suspended particles made sense if liquids were made from moving molecules. The movement also became stronger when temperature increased, as expected if warmer water contained more energetic microscopic motion. Modern instruments can reveal atomic structures and track individual particles under carefully controlled conditions, but ordinary experience already contains many signs of this hidden activity. A smell spreads across a room because molecules move and collide. Food colouring disperses through water because particles undergo molecular motion. Warm air rises because heating changes density and produces bulk movement. A drop of perfume does not remain permanently gathered near the bottle unless the air is completely prevented from mixing, which it rarely is outside an exceptionally strict laboratory. Diffusion is the gradual spreading of particles from regions where they are more concentrated to regions where they are less concentrated. Molecular motion drives this process. Individual particles move randomly, but the overall result is a more even distribution. Diffusion usually occurs faster at higher temperatures because the particles move and interact more energetically. In liquids and solids, diffusion can be slow because particles are crowded or held in structures. Even so, it does occur. Atoms can gradually move through metals, molecules can pass through biological membranes, flavor compounds can spread through food. Given enough time, thermal motion can produce changes that would be invisible during a brief observation. Living cells depend on this microscopic movement. Molecules dissolved in water move through the cell and encounter proteins, membranes, and other molecules. Many biological reactions occur because thermal motion brings the right participants together. The molecules do not usually travel with a detailed plan. They move, rotate, collide, separate, and collide again. Chemical shape and electrical attraction influence which encounters lead to reactions. Temperature strongly affects these processes. At low temperatures, molecular motion becomes less energetic, and many chemical reactions slow down. This is why refrigeration helps preserve food. It does not stop every reaction or every microorganism, but it reduces the rate of many processes that cause spoilage. Heating often speeds reactions by increasing the number of collisions energetic enough to rearrange chemical bonds. Too much heating can damage biological molecules. Proteins depend on particular folded shapes. Increased motion can disrupt the interactions that maintain those shapes. Cooking an egg changes the structure of its proteins, turning the clear liquid white and solid. The atoms have not disappeared, and the substance has not simply dried into place. Energy has allowed molecular structures to unfold and form new connections. Temperature therefore affects not only how quickly particles move, but also what forms of matter remain stable. A solid may melt, a liquid may boil, a protein may unfold, a magnetic material may lose its organized magnetism. At extremely high temperatures, atoms may lose electrons. The restless movement of particles can overcome the forces that maintain a particular structure. Cooling reduces the energy available for these changes, but it does not provide a simple path toward perfect stillness. As matter becomes very cold, quantum effects become increasingly important. Particles cannot always be treated as tiny classical objects following definite paths. Some systems enter unusual collective states in which many particles behave in a coordinated quantum manner. At everyday temperatures, these details are often hidden by constant interactions with the surroundings. A warm object contains so much microscopic activity that delicate quantum patterns are quickly disturbed. Cooling can reduce that disturbance and allow unusual behavior to appear. This is one reason scientists work so hard to reach extremely low temperatures. Cold matter can reveal properties that are difficult or impossible to observe in ordinary conditions. Even near the lowest attainable temperatures, the idea of particles becoming perfectly motionless is not correct. Quantum systems retain a minimum amount of motion or uncertainty. Absolute zero represents the lowest possible thermal state, not a scene in which every particle has become a frozen dot with no activity of any kind. At the other end of the range, extremely hot matter becomes increasingly energetic and less able to maintain familiar structures. Molecules break into atoms, atoms lose electrons, matter becomes a mixture of charged particles known as plasma. In this state, collisions, radiation, and electromagnetic forces distribute energy through a restless population of electrons and atomic nuclei. The Sun is mostly plasma. Its temperature is sustained by energy produced through nuclear reactions in its central region. That energy moves outward through radiation and the motion of matter before eventually leaving the surface as light. Some of that light reaches Earth, where it is absorbed by oceans, soil, buildings, plants, and people. Energy produced by reactions in a distant star becomes microscopic motion in matter around us. The warmth of a sunlit floor and the motion of air molecules in a room are therefore connected to events taking place far away. Yet once the energy is absorbed, the local temperature depends on how it is distributed among the particles in the material. A dark tile may absorb sunlight effectively and warm quickly. A nearby surface may reflect more light and remain cooler. A metal object may spread the absorbed energy rapidly through its structure, while another material keeps most of the warming near the surface. Matter is always receiving, sharing, storing, and releasing energy. The particles within it respond according to the forces between them and the kinds of motion available to them. Gas molecules travel and collide. Liquid molecules jostle and rearrange. Atoms in solids vibrate and pass energy through their structures. More complex molecules rotate, bend, and stretch. Electrons carry energy, absorb radiation, and change states. All of these activities contribute to the thermal condition of matter, but temperature does not follow the motion of every particle separately. It gathers an enormous amount of microscopic detail into one useful measurement. That measurement tells us something stable about a restless system. The next question is how such irregular individual movements become a single temperature that a thermometer can display. A room contains particles moving at many different speeds. A solid contains countless vibrations. A liquid contains rotations, collisions, and changing molecular arrangements. Somehow, from that complicated mixture, physics produces one value that allows us to say that the air is warm, the water is cool, or the metal has reached the same temperature as the hand holding it. Take a sealed glass container filled with air and place it on a table. To the eye, there is very little to see. The glass is still, the air is invisible, and nothing appears to be changing. At the microscopic level, however, the container is crowded with molecules moving in every direction. They cross the available space, collide with one another, strike the walls, rebound, and continue along new paths. Some move faster than others. Some have just lost energy in a collision, others have just gained it. The pattern changes constantly, even while the container looks completely undisturbed. A thermometer placed inside that container gives us one temperature. This may seem surprising. The gas contains an enormous number of molecules, all moving differently, yet the thermometer does not produce a separate reading for every molecule. It gives one value for the gas as a whole. Understanding how those varied motions become one temperature takes us from the behavior of individual particles to the statistical behavior of matter. Temperature is not determined by one unusually fast molecule. It is not determined by the slowest molecule either. It emerges from the way energy is distributed across a large collection of particles. In a simple gas, this distribution is closely related to the average kinetic energy of the molecules. Kinetic energy is the energy associated with motion. When the average kinetic energy rises, the temperature rises. When the average kinetic energy falls, the temperature falls. The word average is essential. Molecules in a gas never settle into one common speed. Even after the gas has been left alone for a long time, its particles continue to have a wide range of speeds. Collisions keep changing them. A fast molecule can strike a slower one and transfer part of its energy. The first molecule may slow down while the second speeds up. Another collision can reverse the situation a moment later. If we could pause the gas and measure every molecular speed, we would find many molecules within a broad middle range. A smaller number would be moving much more slowly, and another smaller number would be moving much more quickly. Restart the gas, wait a fraction of a second, and the identities of those molecules would change. The fast molecule from before might now be slower. A previously slow molecule might have received energy from several collisions. The overall pattern remains stable when the gas is in thermal equilibrium. Individual particles change continuously, but the statistical distribution stays much the same. Temperature describes this stable collective pattern. It allows us to ignore the impossible task of following every collision, and instead describe the condition of the entire sample. This is similar to describing the average speed of traffic on a busy road. Every car has its own speed. Some drivers accelerate, some brake, and one may be moving unusually slowly while searching for the correct exit. The average speed still gives useful information about the traffic as a whole. It does not tell us exactly what each vehicle is doing, but it tells us something meaningful about the group. The comparison has limits because molecules do not drive politely in marked lanes, but it captures the main point. Temperature belongs to the population rather than to one selected particle. A single molecule has energy and motion. A large collection of molecules can have a temperature. This raises an interesting question about very small groups of particles. If only a few atoms are present, their energy can fluctuate significantly from moment to moment. Temperature becomes less stable and less straightforward. The familiar idea of a precise temperature works best for systems containing enough particles that individual variations are smoothed into a dependable average. Everyday objects easily meet this requirement. Even a tiny grain of dust contains an enormous number of atoms. A droplet of water contains more molecules than anyone could count individually. The air inside a small room contains so many particles that statistical descriptions become remarkably reliable. Temperature appears smooth because the microscopic population is so large. A thermometer responds to this population through repeated interactions. Imagine placing a cool thermometer into warm water. Molecules in the water collide with the surface of the thermometer. On average, the warmer water transfers energy into the cooler thermometer. Its internal particles become more energetic, and some measurable property changes. A liquid may expand, and electrical resistance may shift, or infrared radiation may produce a signal in a sensor. The thermometer continues changing until it reaches approximately the same temperature as the water. At that point, energy still moves back and forth between the water and the thermometer, but there is no longer a net transfer in one direction. The two systems have reached thermal equilibrium. Thermal equilibrium is the practical bridge between microscopic motion and temperature measurement. If one object is in equilibrium with a thermometer, and another object is also in equilibrium with that thermometer under the same conditions, then the two objects have the same temperature. This idea allows temperature scales to be built and compared. The thermometer does not measure the speed of every molecule. It responds to the combined effect of countless microscopic exchanges. Its reading is a large-scale sign of the underlying energy distribution. The relationship between motion and temperature is easiest to see in a gas because gas molecules can move freely across the container. In liquids and solids, the situation becomes more complicated. A molecule in a liquid can move through the material, but it's surrounded by neighbours and constantly affected by attractive and repulsive forces. An atom in a solid usually remains close to one position, vibrating within a structure rather than travelling across the object. These different motions still carry energy. In a solid, heating often increases the energy of atomic vibrations. In a liquid, heating can increase movement, rotation, vibration, and the continual rearrangement of neighbouring molecules. In a gas made from complex molecules, energy can be shared between movement through space, molecular rotation, and internal vibration. Temperature therefore cannot always be understood by looking only at how quickly entire molecules travel from one place to another. A molecule may move slowly through space while vibrating strongly internally. Another may rotate rapidly. Energy can occupy several microscopic forms, and collisions can transfer energy between them. Consider a gas made from individual atoms. Each atom can move in 3 spatial directions. It can travel left or right, forward or backward, and upward or downward. Because the atom has no internal bonds, the main thermal activity is its movement through space, along with changes in its electronic state at sufficiently high energies. A gas made from molecules has additional possibilities. The entire molecule can move, but it can also rotate. Its atoms can vibrate relative to one another. At lower temperatures, some of these internal motions may not receive much energy, because quantum rules restrict the available states. As the temperature rises, additional modes of motion can become active. This affects how much energy is needed to raise the temperature of a substance. When matter has more ways to store microscopic energy, added energy can be distributed among more forms of activity. The temperature may then rise more slowly for the same energy input. Water is a familiar example. Water can absorb a large amount of energy without an immediate dramatic increase in temperature. Its molecules interact strongly, and energy can be distributed through their movement, rotation, vibration, and changing network of attractions. This contributes to water having a high heat capacity. A metal pan behaves differently. It may warm quickly on a stove because less energy is required to raise its temperature by the same amount. The details depend on the metal, its mass, and the way energy is transferred, but the underlying reason involves how the material stores microscopic energy. This is why equal heating does not guarantee equal temperature change. Place the same amount of water and cooking oil in similar containers and supply energy at the same rate. Their temperatures will generally rise differently. The particles in each substance have different masses, structures, interactions, and available forms of motion. Temperature tells us how energy is distributed in a system, but it does not by itself tell us the total amount of internal energy. A small cup of boiling water has a higher temperature than a large swimming pool on a mild day. The pool can still contain far more total thermal energy, because it contains vastly more matter. The boiling water has a higher average thermal condition per relevant microscopic degree of freedom. The pool has a lower temperature but an enormous number of molecules. Temperature and total energy answer different questions. One tells us about the thermal state. The other also depends on the amount and nature of the material. Confusing these ideas can lead to strange conclusions. A spark from a fire may reach a very high temperature, yet it contains little total energy because it is tiny. It can cause pain if it lands on the skin, but it does not transfer energy like a large container of hot water. A bathtub of moderately hot water can deliver much more energy because it contains far more matter. The same distinction appears in space. Gas between stars can have an extremely high temperature because its few particles move with great energy. It may still transfer very little energy to an object passing through it because the particles are so widely separated. A person exposed to that gas would not necessarily experience it like dense air at the same temperature. Temperature describes the energy distribution among the particles that are present. It does not tell us how many particles will strike a surface each second. Density and pressure also matter when we want to understand how strongly a hot environment can heat something. The motion behind temperature is random in a particular sense. It lacks a shared large-scale direction. Suppose a sealed box of gas is moving across a room on a trolley. The gas has two kinds of motion at once. The entire box and all its contents move together across the room, while the molecules also move randomly within the box. The motion of the box as a whole does not automatically make the gas hotter. An observer standing in the room sees every molecule carrying the forward speed of the trolley in addition to its random movement. An observer riding on the trolley does not see that shared forward motion. Both observers can still agree on the temperature of the gas because temperature is connected to the random microscopic motion, measured relative to the overall motion of the material. This distinction separates organized motion from thermal motion. A thrown snowball may travel quickly through the air without becoming extremely hot. Its molecules share the forward motion of the snowball, but that organized movement is different from the random movement associated with temperature. When the snowball hits a wall and stops, some of its organized kinetic energy becomes internal energy. The snow deforms, sound is produced, the wall vibrates, and microscopic motion increases slightly. Part of the visible motion becomes thermal motion. Friction does something similar. A sliding book has organized motion across a table. Friction slows the book and transfers energy into microscopic vibrations in the book, the table, and the air. The surfaces warm by a small amount. The energy has not disappeared. It has changed from coordinated motion into less coordinated internal motion. Rub your hands together and the effect becomes easier to feel. Your muscles convert chemical energy into the movement of your hands. Friction then redistributes some of that energy into microscopic motion within the skin. The average thermal energy rises and your hands become warmer. This gives us another way to understand how motion becomes temperature. Not all motion is temperature. A moving object can have large-scale mechanical motion without being hot. Temperature appears when energy is distributed among the internal, largely random movements and interactions of the particles. A rotating wheel has organized motion. Its atoms share a coordinated rotation around the axle. Friction in the bearings gradually disrupts some of that coordination and transfers energy into internal vibrations. The bearings warm, the wheel slows. Ordered movement becomes disordered microscopic movement. The word disorder is useful, but it should not suggest that thermal motion has no rules. Every collision follows physical laws. Energy and momentum are conserved. Electromagnetic forces control how atoms interact. Quantum mechanics determines which energy states are possible. The unpredictability comes from the enormous number of particles and the complexity of tracking them, not from a failure of nature to behave consistently. Even a small sample of gas contains too many molecules for anyone to calculate every path in practical detail. A tiny uncertainty in one collision would spread through later collisions, making long-term individual prediction impossible. Statistical physics handles this problem by describing probabilities and averages. Instead of asking where one molecule will be after 1,000,000 collisions, physicists ask how energy is likely to be distributed across the entire group. The answer is stable enough to define pressure, temperature, and other large-scale properties. Probability also explains why energy spreads from hot matter to cold matter. Place a hot metal block against a cool one. At the boundary, atoms and electrons exchange energy. Individual transfers can occur in either direction. A particle in the cool block may occasionally transfer energy to the hot block. There is no microscopic rule forbidding that single event. The overall transfer still favours the cooler block, because the hot block has more energy distributed among its microscopic states. There are overwhelmingly more ways for the combined system to share energy more evenly than to concentrate even more energy in the already hot block. Over time, the two blocks approach a common temperature. Their energy becomes more evenly distributed, not because every atom reaches the same energy, but because the statistical patterns settle into equilibrium. A dramatic reversal is not completely forbidden at the level of basic mechanics. In principle, particles could move in exactly the right ways for energy to gather spontaneously in one part of the system. The chance is so extraordinarily small for a large object that it never occurs during ordinary experience. A cold cup of tea does not spontaneously become hot while the room cools around it. The direction of thermal change is therefore deeply connected to probability. There are many more microscopic arrangements corresponding to spread out energy than to highly concentrated energy. Matter moves naturally toward the more probable condition. This also helps explain why a thermometer reading remains steady at equilibrium, even though microscopic energy continues to fluctuate. A few particles may become unusually energetic for a moment. A small region may briefly contain slightly more energy than its surroundings. In a large system, these variations are tiny compared with the whole, and disappear quickly through further interactions. In very small systems, fluctuations become more important. A microscopic object can exchange a noticeable fraction of its energy with the surroundings in a short time. Its measured temperature may vary more than the temperature of a large object. Statistical physics still applies, but the smoothness we expect from everyday thermometers becomes less exact. There is another difficulty hidden in the idea of average motion. The average speed of particles and the average energy of particles are not the same kind of average. Faster particles carry disproportionately more kinetic energy than slower ones. A small number of very fast molecules can contribute significantly to the total energy. Physicists therefore connect temperature more directly to average kinetic energy than to average speed. We can understand the principle without calculating it. If molecular speeds generally increase, their kinetic energies rise strongly. Heating changes the entire distribution, giving greater weight to faster motion. The distribution also determines which molecules can escape from a liquid. In a glass of water, molecules have different energies. Some near the surface carry enough energy to overcome attraction from neighbouring molecules and enter the air. Those escaping molecules tend to come from the more energetic part of the distribution. When they leave, the average energy of the remaining water can decrease. The water cools. This is why evaporation removes thermal energy and why sweat helps control body temperature. Wind makes evaporation faster by carrying humid air away from the skin and replacing it with drier air. The faster evaporation allows more energetic water molecules to escape, increasing the cooling effect. A fan does not usually cool the room itself by producing cold air. It increases air movement and helps energy leave the body through convection and evaporation. Humidity changes the effect because air already containing a great deal of water. Vapor cannot accept additional vapor as easily. Sweat then evaporates more slowly. The body may feel hotter even when the thermometer reading is unchanged. These experiences show that temperature is not identical to thermal sensation. The skin responds to energy transfer. Air temperature matters, but so do humidity, air movement, radiation, clothing, and contact with surfaces. The microscopic energy distribution in the environment determines what transfers are possible, while the rate of transfer determines what we feel. Touching metal and wood at the same temperature provides another example. The metal often feels colder because it accepts energy from the skin quickly. Its electrons and atomic structure transport that energy away from the contact point. Wood transfers energy more slowly, so the surface near the hand warms and the rate of energy loss decreases. Your sense of touch may conclude that the metal has a lower temperature, even when a thermometer shows that both materials began at the same value. The hand is detecting energy flow, not reading the average microscopic energy directly. A thermometer also exchanges energy with what it measures, but it is designed to produce a calibrated response. Calibration links a physical change in the thermometer to agreed temperature values. Early thermometers used the expansion of liquids. Modern devices may use electrical resistance, voltage, or emitted radiation. The temperature scale is human-made, but the underlying thermal relationships are not. We choose the numerical labels and divisions. Nature determines which systems reach equilibrium and how their microscopic energy distributions behave. Different temperature scales can describe the same physical condition with different numbers. This is like measuring distance in miles or kilometers. The object does not change when the unit changes. For scientific work, absolute temperature is especially useful because its 0 point corresponds to the lowest possible thermal state. As a system approaches that limit, the simple classical picture of particles slowing toward complete rest becomes unreliable. Quantum mechanics prevents particles from having perfectly fixed positions and perfectly zero motion at the same time. Matter retains a minimum amount of quantum activity. Temperature near absolute zero still describes the distribution of thermal excitations, but those excitations can become rare. Materials may enter unusual states in which ordinary resistance, viscosity, or magnetic behavior changes dramatically. The details belong to the physics of very low temperatures, yet they reinforce an important lesson. Temperature is not merely the visible shaking of tiny solid balls. Particles are quantum objects. Their allowed energies can be discrete. Their collective motions can behave like waves. In solids, vibrations are described as shared excitations moving through the atomic structure. In some systems, groups of particles can act together in ways that have no simple classical comparison. At ordinary temperatures, constant interactions tend to hide much of this quantum behavior. The statistical description remains effective. We can measure temperature, predict energy flow, and understand heating without solving the complete quantum state of every atom. Temperature is one of the great examples of an emergent property. No individual molecule carries the temperature of the room. The temperature appears when countless particles and energy exchanges are considered together. Pressure is similar. One molecule striking a wall produces a tiny force, but it does not create the steady pressure shown on a gauge. Pressure emerges from the combined impacts of many particles. Density emerges from the amount of mass distributed through a volume. Temperature emerges from the statistical distribution of microscopic energy. Emergence does not make temperature unreal. It makes temperature a property that exists at a different level of description. A traffic jam is real even though no individual car contains the traffic jam. A wave on the ocean is real even though each water molecule moves only a limited distance. The wave belongs to the collective behavior. Temperature belongs to matter in much the same way. It summarizes patterns that are invisible when we examine one particle alone. This summary is so dependable that it controls cooking, weather, engines, biology, electronics, astronomy, and nearly every process involving energy. Once motion has been distributed among the microscopic parts of matter, temperature gives us a way to describe the result. The next problem is to identify where that microscopic energy came from. Particles do not simply decide to move more energetically. Energy must be transferred, released, converted, or concentrated. Sunlight, friction, electricity, chemical reactions, compression, and nuclear processes can all supply it, and each route leaves matter warmer through a different chain of events. Once temperature is understood as a description of microscopic energy, another question follows immediately. Where did that energy come from before it became the motion, vibration, and internal activity of matter? The simplest answer is that thermal energy usually comes from another form of energy. Matter becomes warmer when energy is transferred into it, or when energy already present in the system is converted into less organized microscopic motion. A pan warms on a stove because energy moves into the metal. Your hands warm when you rub them because organized movement is converted into internal motion. A battery becomes warm because chemical energy is transformed as electric current moves through its materials. The temperature rises, but energy has not appeared from nowhere. This is an important distinction. Thermal energy is not a basic substance waiting to be released from every object. It is one way energy can be stored and distributed within matter. Energy may begin as motion, light, chemical potential, electrical activity, nuclear binding, or gravitational motion. Through interactions among particles, some of it can become thermal energy. A good place to see this is in friction. Push a heavy box across a rough floor, and both the bottom of the box and the floor may become slightly warmer. The visible motion of the box gradually slows unless you continue pushing. Friction resists the organized movement and transfers energy into the microscopic structure of the two surfaces. Even surfaces that look smooth contain tiny irregularities. Under magnification, they contain ridges, pits, cracks, and raised regions. When the box moves, these features press against one another, bend, break, catch, and release. Atoms near the surfaces are pulled and pushed by electrical forces. Vibrations spread into both materials. Small fragments may be torn away. Some energy also moves into the surrounding air as sound and motion. The box loses organized kinetic energy as its large-scale movement slows. The atoms in the box and floor gain more disorganized microscopic energy. Their temperature rises, usually by an amount too small to notice without sensitive equipment. Rubbing your hands together makes the same conversion easier to detect. Chemical reactions in your muscles provide energy for the movement. Your hands slide across one another, and friction converts part of that organized motion into internal energy in the skin. The molecules in the tissue move and vibrate more energetically, so the temperature rises. The warmth does not come from friction, as though friction were an independent fuel. Friction is the process through which energy is converted. Your body supplies the energy through metabolism. If you stop moving your hands, the energy supply for that particular process ends, and the warmth gradually spreads into the surrounding air and deeper tissue. Brakes on a bicycle or car provide a stronger example. A moving vehicle carries a large amount of organized kinetic energy. When the brakes are applied, pads press against a rotating disc or rim. Friction slows the rotation, and much of the vehicle's kinetic energy becomes thermal energy in the brakes, tires, road, and nearby air. After heavy braking, the components can become extremely hot. The vehicle has not merely lost motion. Its energy has been redistributed into microscopic movement. Some of it also leaves as sound, vibration, and air movement, but heating is one of the main results. Mechanical work can create thermal energy without obvious rubbing. Compressing a gas can make it warmer. Imagine air trapped inside a bicycle pump. As the handle is pushed down, the air is forced into a smaller volume. The moving piston does work on the gas molecules. Molecules collide with the inward moving piston and rebound with more energy. As compression continues, the average microscopic energy of the gas increases. The air becomes warmer, and some of that energy spreads into the pump itself. This is one reason a bicycle pump may feel warm after repeated use. The reverse process can cool a gas. When compressed gas expands and pushes against its surroundings, it can use internal energy to perform work. Its particles may lose energy on average, causing the temperature to fall. Refrigerators and air conditioners make careful use of compression, expansion, evaporation, and condensation to move thermal energy from one place to another. A refrigerator does not produce cold as a substance. It removes energy from the space inside and releases that energy into the room. A fluid called a refrigerant circulates through a closed system. It absorbs energy while evaporating inside the cooling region. A compressor then does work on the refrigerant, raising its pressure and temperature. Outside the cooled space, the refrigerant releases energy and condenses. It is then allowed to expand, lowering its temperature so that the cycle can begin again. This is why the coils or vents at the back of a refrigerator feel warm. They release the energy removed from the food and air inside, along with additional energy supplied by electricity to operate the compressor. Leaving the refrigerator door open cannot cool a closed room. The machine eventually releases more energy into the room than it removes because its motor also produces heat. Electrical energy is another major source of warming. When electric current passes through a material with resistance, moving electric charges interact with the atoms and structure of that material. The charges are driven by an electric field, but they do not move through the material without interruption. They scatter from atoms, defects, vibrations, and other electrons. During these interactions, energy is transferred into the material. Atomic vibrations become more energetic, and the temperature rises. This process is often called resistive heating. An electric kettle uses resistive heating deliberately. Current passes through a heating element designed to resist the flow. Electrical energy is converted into thermal energy in the element. That energy then moves into the water through direct contact and circulation within the liquid. A toaster works in a similar way. Current passes through thin wires with enough resistance that they become very hot. The wires emit visible light and infrared radiation, which transfer energy to the bread. Some energy also reaches the bread through heated air. The bread warms, loses water, and undergoes chemical changes that produce its colour and flavour. Not every warm electrical device is intended to be a heater. Computers, phones, chargers, motors, and batteries often become warm because some electrical energy is converted into thermal energy during operation. Engineers usually try to reduce this unwanted heating because it wastes useful energy and can damage components. A computer processor contains vast numbers of tiny electronic switches changing state rapidly. Electrical energy moves through the circuitry, and interactions within the materials generate heat. Cooling systems carry that energy away using metal conductors, moving air or liquid circulation. Without effective cooling, the processor temperature would rise until performance dropped, or the material was damaged. Electric motors convert electrical energy into organized mechanical motion, but they are not perfectly efficient. Resistance in the wires, friction in bearings, magnetic effects, and air resistance convert part of the energy into heat. The motor may turn a fan or lift a load while also becoming warm. Chemical reactions provide another common route to thermal energy. Chemical energy is associated with the arrangement of electrons and atoms in substances. During a reaction, old bonds are broken, atoms rearrange, and new bonds form. The products may have less stored chemical energy than the reactants. The difference can be released into the surroundings as molecular motion, radiation, or other forms of energy. Burning is a familiar example. When wood burns, substances in the wood react with oxygen. The atoms rearrange into products that include gases, ash, and other compounds. Energy released during the reaction increases the motion of nearby particles and produces light. The hot gases transfer energy to the air and nearby objects. A flame is not a solid object. It is a region where hot gases, reactive molecules, ions, and tiny particles are undergoing rapid chemical changes. Collisions transfer energy among them. Some excited particles emit light. Rising hot gas carries energy upward, while radiation spreads energy in many directions. The original energy was stored in the chemical structure of the fuel and oxygen. For wood, much of that stored chemical energy ultimately came from sunlight. Plants absorbed light and used it to build energy-rich molecules through photosynthesis. Burning the wood releases part of that stored energy, though not by reversing photosynthesis in a simple step. The energy in natural gas, coal, and oil also comes from chemical structures. These fuels formed from ancient biological material that was altered over long periods. Much of their energy can be traced back to sunlight captured by organisms in the distant past. Food provides chemical energy for living bodies. Digestion breaks food into smaller molecules, and cells use controlled chemical reactions to transfer energy into forms that support movement, growth, repair, electrical signaling, and other biological work. No biological process is perfectly efficient, so a significant amount of energy becomes thermal energy. This constant production of heat is part of why the human body remains warm. Even while sleeping, cells continue using energy. The heart beats, breathing muscles move, organs function, and chemical reactions maintain tissues. The body distributes the resulting thermal energy through blood and manages its temperature through sweating, breathing, changes in blood flow, and contact with the environment. Shivering increases thermal energy production by making muscles contract rapidly. The movement may not accomplish useful external work, but it uses chemical energy. Much of that energy becomes internal motion in the body, raising temperature. The process is effective, though it is not especially comfortable and rarely improves anyone's mood. Some chemical processes absorb thermal energy instead of releasing it. Certain cold packs contain substances that react or dissolve in a way that requires energy. That energy is drawn from the pack and its surroundings, lowering their temperature. The pack feels cold because energy moves out of your skin and into the process occurring inside it. Hot packs can use reactions that release energy. In some reusable packs, a liquid rapidly forms crystals after a small trigger is activated. The change in molecular arrangement releases energy, warming the pack. The temperature change comes from energy stored in the previous state and released during the transition. Light can also become thermal energy when matter absorbs it. Radiation carries energy through space without requiring air or direct contact. When light reaches matter, it may be reflected, transmitted, scattered, or absorbed. Absorption transfers energy to the atoms, molecules, or electrons in the material. That energy may initially raise an electron to a different state or increase a particular molecular vibration. Collisions and interactions then spread the energy through the material, where it becomes part of the general thermal motion. Stand in sunlight, and your skin absorbs some of the incoming radiation. The absorbed energy is redistributed among molecules in the tissue, increasing thermal energy. Clothing, skin color, moisture, air movement, and the angle of the sunlight all affect how quickly warming occurs. A dark surface often warms more strongly in sunlight than a light surface because it absorbs more of the incoming visible radiation. A light surface reflects a larger portion. This is a general tendency rather than a guarantee, since the exact behavior depends on the material and the wavelengths involved. Objects also release energy as radiation. Warm matter emits electromagnetic radiation because charged particles within it are moving and interacting. At ordinary temperatures, most of this radiation is infrared and cannot be seen by human eyes. As an object becomes hotter, it emits more energy and the distribution changes. A heating element may first emit invisible infrared radiation. As its temperature rises, it begins to glow dull red, then brighter red, orange, and eventually closer to white, if it becomes hot enough. The glow reflects the thermal energy of the material, though the full behavior also depends on the surface. Radiation allows thermal energy to travel through empty space. The sun warms Earth across the vacuum between them. There is no air extending from the solar surface to our planet to conduct the heat. Energy travels as radiation, is absorbed by matter on Earth, and becomes thermal energy. The sun itself is powered mainly by nuclear fusion. In its central region, atomic nuclei combine under immense pressure and temperature. The resulting nuclei have slightly less mass than the particles that formed them. The difference is released as energy. That energy does not travel directly from the center to Earth in one simple journey. Inside the sun, it is repeatedly absorbed, emitted, and transferred through matter. It moves outward through radiation and the large-scale motion of hot plasma. Energy eventually leaves the visible surface as light, and other radiation then crosses space. When sunlight warms a stone, the immediate source is absorbed radiation. The more distant source is nuclear energy released inside the Sun. The chain between them includes fusion, energy transport through solar plasma, radiation across space, absorption by electrons and atoms, and redistribution through microscopic collisions. Nuclear fission can also produce thermal energy. In a nuclear reactor, certain heavy atomic nuclei split into smaller nuclei after interacting with a neutron. The products move away with considerable kinetic energy and collide with surrounding matter. Their organized motion is quickly distributed into microscopic motion, heating the reactor fuel and nearby materials. That thermal energy can be transferred to water, producing steam that turns a turbine. The turbine drives an electrical generator. The electricity may later power a heater, kettle, computer, or lamp. Energy can pass through several forms before appearing again as thermal motion. Radioactive decay produces heat, as unstable atomic nuclei change into more stable forms. Emitted particles and radiation interact with nearby matter and transfer energy. This process contributes to the internal heat of Earth. Some of the planet's thermal energy comes from radioactive elements decaying within rocks and the mantle. Earth also retains energy from its formation. Early in the history of the planet, matter collided and gathered under gravity. The motion of falling material was converted into internal energy during impacts and compression. Dense materials sank toward the center, releasing more gravitational energy. Although Earth has cooled over billions of years, significant internal heat remains. Pressure deep inside Earth also affects temperature. As matter is buried beneath layers of rock, it is compressed. Gravitational energy and mechanical work contribute to the high temperatures found far below the surface. Heat moves slowly outward through conduction, convection within the mantle, volcanic activity, and the circulation of hot fluids. Gravity can heat matter on much larger scales. When a cloud of gas collapses under its own gravity, particles accelerate inward. They collide, and their organized inward motion becomes thermal energy. The gas temperature rises. This process is important in the formation of stars. A large cloud of gas contracts, converting gravitational potential energy into motion and then heat. As the central region becomes denser and hotter, conditions may eventually allow nuclear fusion to begin. Gravity supplies the initial heating, while fusion later becomes the main long-term energy source. A similar process can occur when gas falls toward a compact object such as a dense star or black hole. The gas accelerates, collides with other matter, and forms a hot rotating structure. Friction, turbulence, compression, and magnetic interactions convert gravitational energy into thermal energy and radiation. Matter can become extremely hot before crossing any boundary from which light cannot escape. Impacts are another direct way to create heat. Drop a ball onto the floor and it may bounce, but each bounce is lower than the last. Some of the ball's gravitational and kinetic energy becomes sound, deformation, and microscopic motion in the ball and floor. A small impact produces too little heating to notice. A large impact can produce enormous temperatures. Meteoroids entering an atmosphere compress gas in front of them and experience interactions that heat both the object and the surrounding air. When a large object strikes a planet, its kinetic energy can melt or vaporize rock. Pressure and rapid deformation contribute to this heating. Matter is forced into new arrangements faster than energy can escape. Atomic vibrations increase, chemical bonds break, and parts of the material may change phase. Phase changes can absorb or release energy without immediately changing temperature. Melting ice requires energy, because water molecules must move out of the ordered solid structure. During steady melting, incoming energy is used mainly to change the arrangement rather than raise the temperature. Freezing releases energy. As water molecules settle into the solid structure of ice, energy is transferred to the surroundings. This is why a freezer must remove energy not only to cool water to its freezing temperature, but also to complete the change into ice. Evaporation requires energy because molecules must separate from the liquid. Condensation releases energy when gas molecules return to the liquid state and form stronger interactions with neighbouring molecules. These transfers are important in weather. Water evaporating from an ocean absorbs energy. Winds carry the vapour to other places. When the water condenses into cloud droplets, energy is released into the atmosphere. This can strengthen rising air and contribute to storms. Thermal energy is moved across large distances through changes in the state of water. Not every source of temperature involves energy entering from outside. Sometimes a system already contains energy, but that energy changes form or becomes distributed differently. A compressed spring stores energy in its shape. If released in a way that drives friction, the stored energy eventually becomes heat. A stretched rubber band can warm when rapidly contracted because its molecular structure changes and energy is redistributed. Mixing substances can also change temperature. Molecules that were separated may form new interactions when combined. If the new arrangement has lower stored energy, the difference may appear as thermal energy. If creating the mixture requires energy, the temperature may fall as energy is drawn from molecular motion. The same principle applies throughout these examples. Thermal energy is not a special final substance produced by unrelated tricks. It is energy distributed among microscopic motions, interactions, vibrations, rotations, and internal states. Many pathways can lead to that distribution. Mechanical motion can be randomized through friction and impact. Electrical energy can be transferred through resistance. Chemical energy can be released through reactions. Radiation can be absorbed. Gravitational energy can be converted during collapse and compression. Nuclear changes can release energy from atomic nuclei. Phase transitions can absorb or release energy as matter rearranges. Once energy enters the microscopic population, collisions and interactions spread it. A few particles may receive the energy first, but they rarely keep it for long. They strike neighbours, excite vibrations, emit radiation, or transfer energy through electrons. The material moves toward a new thermal distribution. How much the temperature changes depends on more than the amount of energy supplied. It depends on the mass of the object, its composition, its physical state, and the microscopic ways in which it can store energy. The same energy input may make one material extremely hot, while producing only a modest change in another. The speed of energy transfer matters as well. A material may receive energy quickly but also lose it quickly. A thin metal object in a flame can heat rapidly and cool rapidly. A large body of water warms slowly and can remain warm for much longer. This begins to explain a common puzzle. Two objects can receive the same energy, reach the same measured temperature, or sit in the same room for hours, yet feel very different when touched. The difference does not necessarily come from one object secretly having a lower temperature. It often comes from how quickly each material can take energy from the skin, how much energy it can absorb, and how efficiently it carries that energy away from the point of contact. A metal railing and a wooden fence can stand beside each other through the same cold night. By morning, both have spent hours surrounded by the same air. A thermometer placed against either surface may show nearly the same temperature, yet when you touch them, the metal feels much colder than the wood. On a hot day, the same metal can feel more dangerously hot than a nearby wooden surface, even when both have been exposed to the same sunlight. The difference is not necessarily temperature. It is the speed at which energy moves between the material and your skin. Human touch does not work like a thermometer. The nerves in the skin respond to temperature, but they also respond strongly to changes in temperature and to the rate at which energy enters or leaves the body. When you place a warm hand on a cool object, energy begins moving from the skin into the object. If that transfer happens rapidly, the temperature of the skin falls quickly and the object feels very cold. If the transfer is slow, the skin remains closer to its original temperature and the object feels less cold. Metal usually conducts thermal energy well. energy entering the surface from your hand is quickly carried away into the rest of the metal. The area beneath your fingers does not remain warm for long because the energy spreads deeper into the object. More energy can then continue leaving your skin. Wood is a poor thermal conductor. When your hand touches it, the thin layer of wood directly beneath your skin warms, but the energy does not travel away very quickly. The warmer surface layer reduces the temperature difference between your hand and the wood. The energy transfer slows, so the wood feels less cold. This is why the floor beside a bed may produce two very different sensations. A wooden floor can feel cool but manageable. A tile or stone floor at the same room temperature may feel much colder. The tile accepts energy from your feet more quickly and carries it away from the point of contact. Your skin responds to that rapid loss. The process reverses when the object is hotter than the body. Touch warm wood and energy enters the skin relatively slowly. Touch metal at the same temperature and the transfer can happen much faster. The metal feels hotter because it delivers energy to the skin more efficiently. This is also why a metal baking tray can cause a burn much faster than warm air inside an oven. The air may be at a high temperature, but air is not very dense and does not conduct thermal energy efficiently. Only a limited number of air molecules collide with the skin at any moment. A metal tray contains far more particles in close contact and can transfer energy rapidly into the tissue. The temperature is important, but it is not the only factor. The material, contact area, duration, pressure, moisture, and condition of the skin all affect how much energy moves and how quickly it moves. A brief touch may not last long enough to transfer a dangerous amount of energy. Continued contact allows more energy to enter or leave. Pressing firmly against a surface creates better contact by reducing tiny air gaps. Wet skin often transfers energy more effectively than dry skin, because water fills spaces between the skin and the material. This is why a hot object can be more dangerous when steam or liquid water is involved. Hot air may feel uncomfortable, but hot water transfers energy into the body much more efficiently. Steam can be especially dangerous because it releases additional energy when it condenses into liquid on the skin. The water molecules in steam are separated as a gas. When they contact a cooler surface and condense, they form stronger attractions with one another. Energy is released during this change. The skin receives energy both from the high temperature of the water and from the condensation process. Boiling water and steam may be associated with the same boiling temperature under ordinary conditions, but steam can deliver more energy because of the phase change. The thermometer reading alone does not tell the whole story. The same principle appears at lower temperatures. Cold air and cold water do not feel equally cold. Step outside into chilly air, and the body can remain comfortable for some time with suitable clothing. Enter water at the same temperature, and energy leaves the body much faster. Water conducts energy better than air, and has a much greater capacity to absorb it. It also remains in close contact with the skin. Moving water continually replaces the thin, warmed layer beside the body with colder water, maintaining rapid heat loss. Air trapped in clothing behaves differently. It warms near the skin and moves very little. Because still air is a poor conductor, it slows the loss of thermal energy. Thick clothing works largely by trapping many small pockets of air. The fibers of wool, fleece, and other insulating materials do not need to create heat. Their job is to prevent the energy produced by the body from escaping too quickly. A coat left on a chair has no special warmth of its own. Once worn, it traps air and reduces energy transfer from the body to the colder surroundings. Compressing insulation can make it less effective. When a thick jacket or sleeping bag is squeezed, some of the trapped air is pushed out. The material becomes thinner and energy can travel through it more easily. This is why insulation beneath a sleeping person may matter as much as insulation above them. Body weight compresses the layer underneath, reducing its ability to trap air. A metal surface has the opposite character. Its atoms and mobile electrons allow energy to move through the material quickly. Metals feel cold because they remove energy efficiently, and they feel hot because they supply it efficiently. Different metals also conduct energy at different rates. Copper and aluminium are effective conductors, which is why they are often used in cookware and cooling systems. Stainless steel generally conducts less effectively than copper, though it is useful because it is strong, durable, and resistant to corrosion. Cookware is often made from several materials combined in layers. A metal that spreads energy quickly may form the inner core, while another material provides a durable cooking surface. The aim is to distribute energy evenly, so that one area does not become far hotter than the rest. A thin metal pan can change temperature quickly because it contains relatively little material. A heavy pan may take longer to warm, but once heated it can hold more energy and maintain a steadier temperature when food is added. This introduces another reason some matter feels hotter than other matter. Materials differ in how much energy they can store for a given change in temperature. This property is known as heat capacity. When comparing equal amounts of different substances, physicists often discuss specific heat capacity. Water has a high specific heat capacity. It can absorb a large amount of energy, while its temperature rises relatively slowly. Metals usually require less energy for the same rise in temperature. This does not mean water is always safer to touch. A container of hot water can hold a large amount of thermal energy and transfer it efficiently to the skin. The high heat capacity means its temperature does not fall quickly when it begins warming another object. Imagine a metal spoon and a bowl of soup at the same temperature. The spoon may feel sharply hot when touched, but its temperature can drop quickly because it has little mass and limited stored energy. The bowl of soup contains much more matter and may hold far more thermal energy. Contact with it can continue transferring energy for much longer. The amount of matter matters. A tiny spark can have a very high temperature, but it contains little total energy. It may sting or cause a small burn, yet it cannot heat the body like a large quantity of hot liquid. A bath filled with moderately hot water may have a lower temperature than the flame of a match, but the bath contains vastly more thermal energy. The flame can heat a small region quickly. The water can transfer energy across a large area and continue doing so for a long time. Density also affects how matter feels. Dense materials place more particles near the contact surface. They often contain more thermal energy within a given volume than less dense materials at the same temperature, though the exact result depends on composition and heat capacity. Air is sparse compared with water or metal. Its molecules are separated by large distances relative to their size. Even when the molecules are moving rapidly, there are fewer of them available to collide with the skin. This helps explain how people can briefly enter a very hot sauna without suffering the injury that would occur in water at the same temperature. The hot air transfers energy less efficiently than hot water. Sweat also evaporates from the skin, carrying energy away. Touching a metal bench inside that same sauna would be far more dangerous. The bench and the air may have reached a similar temperature, but the metal can transfer energy into the body much faster. Air movement changes the experience. When the surrounding air is cooler than the skin, wind carries away the layer of air that the body has already warmed. Fresh, cooler air replaces it, allowing energy loss to continue rapidly. This is why windy weather feels colder than calm weather at the same measured air temperature. The effect is often described as wind chill. The wind does not make an exposed object colder than the actual air temperature through this mechanism alone. It makes the object cool toward that temperature more quickly. For living skin, that faster energy loss creates a lower apparent temperature and increases the risk of cold injury. A fan works through a related process. It moves air across the body, increasing convection and helping sweat evaporate. The room temperature may stay almost unchanged, but the person feels cooler because energy leaves the skin faster. Once the air becomes hotter than the skin, moving air can begin adding energy to the body rather than removing it. Evaporation may still provide cooling if the air is dry enough, but the balance becomes more difficult. In very hot and humid conditions, a fan may offer less protection because sweat cannot evaporate effectively. Humidity matters because evaporation requires water molecules to leave the skin and enter the air. Dry air can accept more water vapor. Humid air already contains a large amount, so evaporation slows. When sweat remains on the skin without evaporating, it provides much less cooling. A person may feel hotter at the same air temperature because the body cannot release energy as efficiently. The measured temperature has not changed, but the conditions for energy transfer have. Moisture changes contact with cold materials as well. Wet clothing loses much of its insulating ability because water replaces trapped air. Water conducts energy more effectively than air and can move through the fabric, carrying energy away from the body. This is why wet clothes can become dangerous in cold weather. The fabric may still cover the skin, but it no longer provides the same barrier to energy loss. Evaporation from the wet material can remove additional energy. The skin itself is not a uniform thermometer. Different regions of the body have different numbers and types of temperature-sensitive nerve endings. The fingers, face, and lips may respond more strongly than other areas. Blood flow also changes the local temperature and affects what a surface feels like. Cold conditions cause blood vessels near the skin to narrow. This reduces warm blood flow to the surface and helps conserve energy in the body core. The skin becomes cooler, especially in the hands and feet. A material that felt only mildly cool earlier may then feel much colder. Warm conditions cause vessels near the skin to widen. More blood reaches the surface, allowing energy to move into the environment. The skin becomes warmer and may react differently to contact. Previous exposure changes sensation. Place one hand in cool water and the other in warm water for a short time, then move both into water at an intermediate temperature. The hand that was cooled may report that the water feels warm. The hand that was warmed may report that it feels cool. The water has one temperature. The difference comes from the thermal condition of each hand and the recent adaptation of the nerves. Energy enters one hand and leaves the other. This is why touch is useful for comparison but unreliable for precise measurement. The nervous system is mainly interested in protecting the body, not producing an objective laboratory reading. It warns about rapid energy transfer and tissue damage. Pain from extreme heat and cold can also become difficult to distinguish. Both can damage cells, disrupt proteins, affect blood flow, and activate pain receptors. A very cold object may initially feel as though it is burning. Cold metal can stick to wet skin because the metal removes energy rapidly. Water at the surface freezes, forming a bond between the skin and the metal. Pulling away can damage the tissue. The metal is not chemically sticky. Its high conductivity allows freezing to occur quickly. Materials can also feel warmer or cooler because of their surface texture. A rough surface may touch only certain points on the skin, leaving small pockets of air between them. A smooth surface may create more complete contact, allowing faster energy transfer. Soft materials can conform to the shape of the body and increase contact area, but many soft materials also trap air and conduct poorly. The final sensation depends on several competing effects. Stone, glass, ceramic, and metal often feel cold because they conduct energy better than fabric, foam, or wood. A polished stone countertop can draw energy from the hand quickly. A thick carpet at the same temperature transfers energy slowly because its fibers trap air. The carpet does not have a higher temperature. Its structure simply makes it difficult for thermal energy to move. The same structural differences affect buildings. Stone and concrete can absorb large amounts of energy during the day and release it slowly later. Lightweight materials may warm and cool more quickly. Insulation slows energy transfer through walls and roofs by trapping air or gas in materials that resist conduction. A room can contain surfaces at similar temperatures but still feel different depending on the walls and windows. The body exchanges energy not only through direct contact and move-in air, but also through radiation. Stand near a cold window on a winter night, and you may feel chilled even when the room air is comfortable. Your body emits infrared radiation. The cold window sends less radiation back than a warmer wall would, so the net energy loss from your body increases. A fireplace can make you feel warm from across a room, because radiation travels directly from the hot flames and surrounding materials to your skin. The air between you and the fire does not need to become equally hot first. This is why temperature comfort depends partly on the temperatures of surrounding surfaces. Two rooms with the same air temperature can feel different if one has cold walls and windows, while the other has warmer surfaces. Sunlight produces the same direct effect outdoors. The air temperature may be cool, but absorbed sunlight adds energy to clothing and skin. Step into shade and the energy input drops immediately, even though the air has not suddenly changed temperature. Colour and surface finish can influence absorption and emission. Dark, dull surfaces often absorb visible light effectively. Shiny surfaces may reflect more radiation. In the infrared range, the details depend on the material, and a surface that looks bright to human eyes may behave differently at invisible wavelengths. A reflective emergency blanket reduces energy loss mainly by reflecting infrared radiation back toward the body. It is very thin and does not contain much insulating material, but it can reduce one route by which thermal energy escapes. It works best when used with other protection that also limits wind and conduction. Cooking provides many examples of materials feeling and behaving differently at the same temperature. An oven heats food through hot air, radiation from the walls and heating elements, and contact with a tray or dish. The outer surface may become hot before the centre, because energy must travel inward. A metal tray transfers energy efficiently into the base of the food. A glass or ceramic dish heats differently and may retain energy longer after removal. Microwave heating follows another route. Microwaves interact with electric charges and polar molecules in food, producing molecular movement and internal energy. Water-rich regions often absorb energy effectively, though the exact heating pattern depends on the shape, composition, and location of the food inside the appliance. The plate may feel cooler than the meal because it absorbs less microwave energy directly. It can still become hot through contact with the food. A dry ceramic handle may remain manageable while a wet section becomes much hotter. Frozen food can contain both cold and very hot regions after uneven heating. The average temperature is not enough to guarantee that every part is safe. Energy may be concentrated in some areas, while others remain frozen. Uneven energy distribution is temporary. Given enough time, thermal energy spreads from hotter regions to cooler ones. The speed of this process depends on the material, thickness, shape, and surrounding conditions. A thick piece of food cools slowly at its centre, because energy must travel through the material to reach the surface. A thin layer cools more quickly because every part is close to the surroundings. Breaking something into smaller pieces increases the surface area available for energy transfer. A hot drink cools faster when poured into a wide, shallow container than when left in a narrow, insulated mug. The larger exposed surface allows more evaporation, convection, and radiation. Stirring can also increase cooling by bringing warmer liquid from the centre to the surface. A metal spoon left in the drink provides another route for energy to leave. The spoon conducts energy from the liquid into the handle and surrounding air. The effect may be modest, but the direction is clear. The sensation of hot and cold therefore depends on an entire chain of events. Matter has a temperature because energy is distributed among its microscopic parts. Touch brings two systems into contact. Energy begins moving according to their temperature difference and material properties. The skin changes temperature, nerves respond, and the brain interprets the signal. A material feels hotter when it transfers energy into the skin quickly. It feels colder when it removes energy quickly. Low conductivity can make an object feel mild even when its temperature differs significantly from the body. High conductivity can make the same difference feel severe. Heat capacity determines how long the object can maintain the transfer. Density and mass affect how much energy is available. Surface texture and moisture affect contact. Air movement changes convection. Humidity changes evaporation. Nearby surfaces affect radiation. Blood flow and previous exposure alter the response of the body. None of this makes the sensation false. Feeling is the body's practical report about energy exchange. It simply answers a different question from a thermometer. A thermometer asks about the thermal state of the material. The skin asks what the material is doing to the body right now. The answer can change even while the measured temperature remains steady. A still room becomes cooler to the skin when a fan begins moving air. A dry day becomes more uncomfortable as humidity rises. A metal tool and a wooden handle provide different sensations despite sharing the same surroundings. Those differences become even more pronounced when matter changes its physical state. Particles in a solid are constrained differently from particles in a liquid. Gas molecules are far more separated, while plasma contains charged particles moving and interacting under electrical and magnetic forces. Each state stores and transfers thermal energy in its own way, which is why the behavior of temperature becomes especially revealing when solids melt, liquids boil, gases expand, and atoms begin to lose their electrons. The differences between solids, liquids, gases, and plasma begin with the same particles but very different arrangements. An iron bar, a pool of molten iron vapor, and an extremely hot cloud of charged iron particles are all made from the same chemical element. What changes is the way energy is distributed and whether the particles remain bound together in a stable structure. Temperature influences these arrangements, but it does not act alone. Pressure, density, chemical composition, and the forces between particles also matter. Water can be solid, liquid, or gas depending on both temperature and pressure. Other substances follow their own patterns. Some melt easily, some require intense heating, and some change directly from solid to gas under suitable conditions. A solid maintains a definite shape because its particles are held in a stable arrangement. In many solids, atoms form an ordered crystal structure. Each atom remains near a particular position relative to its neighbours. It does not remain perfectly still. It vibrates around that position. These vibrations are part of the thermal energy of the solid. When the solid is cold, the vibrations are less energetic. When the solid is heated, they become stronger. The atoms move farther from their average positions, and the forces between them continually pull and push them back. A crystal is not perfectly rigid at the microscopic level. It is an active structure in which the motion of one atom influences nearby atoms. Vibrations can spread through the material. Thermal energy moves from a warmer region to a cooler region through these connected motions. In metals, mobile electrons also carry energy. They move through the structure and interact with atoms and other electrons. This helps metals conduct thermal energy quickly. It also helps explain why a metal rod can warm along its length, even though the atoms themselves remain close to their original positions. Different solids respond to heating in different ways. A metal may expand gradually as the average spacing between atoms increases. Glass may soften over a range of temperatures. Rubber may become more flexible or lose its strength. Wood may dry, darken, release gases, and eventually burn before it ever becomes a simple liquid. The microscopic structure determines what happens. A pure crystalline material may have a well-defined melting temperature under a fixed pressure. A complex material containing many different substances may soften, decompose, or react rather than melt neatly. When a solid is heated, its temperature usually rises at first. The added energy strengthens atomic vibrations and other internal motions. As the material approaches its melting condition, the situation changes. Energy begins disrupting the structure that keeps the particles in fixed relative positions. During steady melting, energy can enter without producing a large rise in temperature. The energy is being used to change the arrangement of the particles. The ordered solid structure breaks down, and the particles gain enough freedom to move around one another. This does not mean that all attractions disappear. In a liquid, particles remain close together. They still pull and push on their neighbours. They simply no longer stay in one permanent arrangement. A block of ice provides a familiar example. Heating the ice increases its microscopic activity. At the melting point, additional energy allows the ordered structure to collapse. The water molecules become able to rearrange and flow. The liquid water is not necessarily hotter than the ice while melting is taking place. Solid and liquid can exist together at the same temperature. The difference lies in their structure and energy distribution. Once all the ice is melted, continued heating raises the temperature of the liquid. The molecules move, rotate, vibrate, and change neighbours more energetically. Water is especially interesting because the attractions between its molecules are strong enough to influence many of its thermal properties. These interactions help water absorb a large amount of energy without a rapid rise in temperature. They also give water an unusual density pattern. Most substances become denser as they cool and enter the solid state. Water reaches its greatest density while still liquid, then expands as it freezes into an open crystal structure. Ice therefore floats on liquid water. This may seem like a small detail, but it has major consequences. Lakes and ponds tend to freeze from the surface downward. The floating ice forms an insulating layer, slowing further energy loss and allowing liquid water to remain below. Temperature in a liquid is more complicated than the simple speed of molecules moving through space. Molecules also rotate and vibrate. Energy is stored in their interactions. The liquid constantly rearranges, creating and breaking temporary local structures. A glass of water that appears still contains continuous microscopic motion. Molecules move in all directions. They collide, turn, and exchange energy. Some reach the surface and escape into the air. Evaporation can occur at almost any ordinary liquid temperature. The molecules do not all have the same energy. Some near the surface are energetic enough to overcome the attractions holding them in the liquid. They leave as vapor and carry energy away. The remaining liquid can become cooler because the escaping molecules often come from the more energetic part of the population. This is why water evaporating from skin produces cooling. It is also why a wet surface can become cooler than the surrounding air under dry and breezy conditions. Boiling begins when vapor can form throughout the liquid rather than only at the surface. Bubbles appear because the pressure of the vapor becomes sufficient to resist the pressure around it. The boiling temperature depends on external pressure. At lower atmospheric pressure, water boils at a lower temperature. This is why cooking can take longer at high altitude. The boiling water is not as hot, even though it appears just as active. Inside a pressure cooker, the pressure is higher. Water can remain liquid at a higher temperature before boiling strongly. Food cooks faster because it is exposed to hotter water and steam. Boiling does not mean that the molecules have reached a maximum possible temperature. It means the liquid is changing into gas under the existing pressure. If the vapor is heated after leaving the liquid, its temperature can continue rising. A gas differs from a liquid mainly because its particles are much farther apart and are not held together as one continuous volume by strong attractions. Gas particles travel through the available space, colliding with one another and with the walls of any container. A gas has no fixed shape and no fixed volume. It spreads to fill the space available to it. If more space becomes available, the particles occupy it. If the gas is compressed, the particles are forced closer together. Temperature in a simple gas is closely connected to the average energy of this motion. Warmer gas particles move more energetically on average. They strike container walls more frequently and with stronger effects. If the gas is held in a rigid sealed container and heated, the pressure rises. The particles cannot spread into a larger volume, so their more energetic collisions increase the force on the walls. If the container can expand, heating may cause the gas to occupy more space instead. A balloon grows when the gas inside pushes outward, strongly enough to stretch the material. The final size depends on the gas temperature, the outside pressure, and the resistance of the balloon. This relationship explains why warm air tends to rise in cooler surroundings. When air is heated and allowed to expand, it becomes less dense. A volume of warm air contains less mass than the same volume of cooler air at the same pressure. The surrounding denser air pushes underneath it, and the warmer air rises. The rising motion is not caused by hot particles deciding that the ceiling looks inviting. It comes from differences in density and pressure within gravity. The result drives convection in rooms, cooking pots, the atmosphere, oceans, and the interiors of stars. As warm fluid rises, cooler fluid moves in to replace it. This creates circulation. In a pot of water on a stove, energy enters near the base. The warmer water expands slightly, becomes less dense, and rises. Cooler water descends. The motion helps distribute energy through the pot. Convection occurs in liquids and gases because the particles can move in bulk. Solids cannot circulate in the same ordinary way, though very hot solid material can deform and flow slowly over long periods. Earth's mantle is mostly solid rock, yet it can move gradually enough to transport energy through the planet. Gas can cool during expansion even without losing energy directly to a colder object. When a gas expands and pushes against its surroundings, it performs work. Part of its internal energy is used in that process, so the average thermal energy may fall. Rising air in the atmosphere expands as the surrounding pressure decreases. The expansion cools the air. If it cools enough, water vapor can condense into droplets, forming clouds. Condensation releases energy, which can affect the continued motion of the air. Falling air is compressed by increasing pressure and tends to warm. These temperature changes contribute to weather patterns, winds, cloud formation, and dry regions on the far side of mountain ranges. A gas can also become extremely hot while remaining very thin. Temperature tells us about the average energy of the particles, not how many particles are present. A sparse gas in space may have particles moving at tremendous speeds and therefore have a high temperature. Because there are so few particles, it may transfer energy slowly to an object placed within it. This distinction becomes essential when discussing plasma. Plasma is often described as the fourth state of matter, although matter can form several other unusual states under extreme conditions. Plasma forms when enough energy is supplied to separate electrons from atoms. An ordinary gas usually contains neutral atoms or molecules. Each atom has negatively charged electrons associated with a positively charged nucleus. At sufficiently high temperatures, collisions become energetic enough to remove some electrons. The result is a mixture of free electrons and positively charged ions. This mixture is plasma. Because its particles carry electric charge, plasma behaves differently from an ordinary gas. Electric and magnetic fields can guide its motion. Charged particles can produce currents, waves, and complex collective patterns. A flame may contain a small amount of plasma, but most familiar flames are not fully ionized. Lightning contains a much more strongly ionized path through the air. The electrical discharge rapidly heats the gas, separates electrons from atoms, and creates a conducting plasma channel. The air in a lightning channel can reach an extremely high temperature in a very short time. It expands suddenly, producing a pressure wave that becomes thunder. The flash fades quickly, but the energy has already been transferred into light, sound, chemical changes, and thermal motion. The sun and other ordinary stars are mostly plasma. Their temperatures are high enough that atoms cannot remain neutral throughout much of their interiors. Electrons and nuclei move through a dense, charged environment. Temperature within a star affects pressure, fusion reactions, radiation, and the overall balance that holds the star together. Gravity pulls the plasma inward. Pressure produced by hot matter and radiation pushes outward. A stable star spends much of its life in a balance between these tendencies. The visible surface of the Sun is cooler than its central region, yet still hot enough for matter to behave very differently from materials on Earth. Above that visible surface lies a thin outer atmosphere that reaches much higher temperatures. The reason for this heating involves magnetic fields, waves, and energy released by changes in the solar plasma. Plasma does not need to be extremely hot in every case. Some plasmas are described as cold because the electrons have much more energy than the heavier ions and neutral particles. The system is not in simple thermal equilibrium. This shows that assigning one temperature to matter can become difficult when different parts of the particle population have different energy distributions. Electrons may have one effective temperature while ions have another. A thermometer placed in such an environment would interact with these particles in complicated ways. Ordinary solids, liquids, and gases often move toward internal equilibrium quickly enough that one temperature describes them well. Plasma can maintain more complicated conditions because charged particles interact over longer distances and respond strongly to fields. Even an ordinary gas may fail to have one clear temperature if it has just been disturbed. Imagine injecting a beam of very fast particles into a cooler gas. For a while, the system contains two distinct populations. The fast particles have not yet shared their energy evenly with the rest. After enough collisions, the energy spreads, and a stable thermal distribution may form. Only then does one temperature become a reliable summary of the whole gas. A similar issue appears inside a material that is being heated rapidly. The surface may become hot before the center. Electrons may receive energy before the atomic structure does. Different parts of the object can temporarily have different temperatures. Thermal equilibrium is not instantaneous. Energy needs time to move through matter. That time depends on conductivity, thickness, density, heat capacity, and the method of heating. Place a thick piece of metal in a flame and the outside warms first. Energy then travels inward. Because metal conducts well, the temperature difference may shrink relatively quickly. A thick piece of wood responds more slowly, and its surface may begin decomposing before the center becomes very hot. Heat a container of soup, and the liquid can circulate, carrying energy from one place to another. A thick, solid food cannot circulate in the same way, so energy must move inward through conduction. Its outside can become dangerously hot while the center remains cool. The state of matter changes not only how energy is stored, but also how it moves. In solids, conduction is usually the main internal process. In liquids and gases, conduction occurs alongside convection. In plasma, charged particle motion, electromagnetic waves, radiation, and magnetic fields can all transport energy. Radiation is present in every state. All matter above the lowest possible temperature emits electromagnetic radiation. The amount and type depends strongly on temperature and surface properties. A warm solid in a room emits mostly infrared radiation. A hot metal object begins glowing visibly. Very hot plasma may emit visible light, ultraviolet radiation, X-rays, and other wavelengths. Radiation can carry energy away from matter without direct contact. It can also deliver energy when absorbed. A solid surface warmed by sunlight receives radiation from the sun. A gas may absorb particular wavelengths depending on its molecules. Plasma interacts with radiation through its free charges and ions. Changing state requires energy because particles must enter a different arrangement. Melting separates particles from fixed positions. Vaporization pulls them away from the liquid. Ionization removes electrons from atoms. When the reverse changes occur, energy is released. Freezing forms a more ordered solid structure. Condensation brings gas particles into a liquid. Recombination allows electrons to return to ions, often producing radiation. These processes can happen while temperature changes slowly or remains nearly constant. A pot of boiling water continues absorbing energy, but much of that energy goes into creating vapor. The water does not simply become hotter without limit, while liquid and vapor remain together at the boiling pressure. This is why the sight of violent boiling can be misleading. A gently boiling pot and a vigorously boiling pot may contain liquid at nearly the same temperature. The stronger heat source causes more water to change into vapor each second rather than greatly increasing the liquid temperature. Ice behaves in the same way during melting. Adding energy increases the rate at which solid becomes liquid. Once the solid is gone, continued energy input raises the liquid temperature again. Other materials have different transition conditions. Carbon dioxide at ordinary atmospheric pressure changes directly between solid and gas. The solid is often called dry ice because it does not leave a pool of liquid under normal room conditions. As dry ice absorbs energy, carbon dioxide molecules escape into the gas phase. The cold gas can cause water vapor in the air to condense into visible droplets, creating the familiar low fog used in demonstrations and theatrical effects. Under different pressure, carbon dioxide can exist as a liquid. The state is determined by the combination of temperature and pressure rather than by temperature alone. At very high pressure, familiar distinctions can become less simple. A substance may enter a state in which the difference between liquid and gas disappears. It can flow like a dense fluid, while filling available space more like a gas. Matter also has states beyond the usual four. At very low temperatures, some particles can enter collective quantum states. Under immense pressure, matter can form arrangements unlike ordinary solids. Inside dense stars, electrons and nuclei can be compressed into unusual conditions. The common states remain useful because they describe most matter encountered in everyday life. Solids hold their shape, liquids flow while keeping a volume, gases spread through their containers, and plasmas contain enough charged particles to respond collectively to electric and magnetic forces. Temperature affects all of them, but its meaning must be connected to the motions available in each state. In a gas, movement through space is especially important. In a solid, vibrations and electronic activity dominate much of the thermal behavior. Liquids combine movement with strong interactions and constant rearrangement. Plasma adds ionization and long-range electromagnetic effects. The particles themselves do not carry labels saying solid, liquid, gas, or plasma. The state emerges from how they interact, how much energy they have, and the conditions around them. A water molecule in ice is still a water molecule. In liquid water, it has greater freedom to change neighbours. In water vapour, it moves largely independently across much greater distances. If enough energy is supplied, the molecule can break apart, and its atoms can eventually become ionized. The journey from solid to plasma does not happen in one universal sequence for every material. Some substances decompose chemically before boiling, some lose electrons while still extremely dense, some exist only under narrow ranges of pressure and temperature. The broad pattern is still clear. Adding energy tends to activate more kinds of motion and weaken the structures that keep particles together. Removing energy tends to reduce accessible motion and allow stronger organization to appear. Continue removing energy and matter approaches conditions far outside ordinary experience. Molecular motion becomes less energetic. Gases condense. Liquids freeze. Atomic vibrations diminish. Familiar thermal noise becomes quieter, and subtle quantum behavior that was previously hidden begins to control the material. Cooling can produce superconductors that carry electric current without ordinary resistance, fluids that move without ordinary viscosity, and groups of atoms that behave as a shared quantum system. Reaching those conditions requires more than placing something in a household freezer. Scientists must remove energy through a sequence of specialized methods, each taking matter closer to the lowest temperatures nature permits. As energy is removed from matter, the motion and internal activity of its particles become less energetic. Gases may condense into liquids. Liquids may freeze into solids. Atomic vibrations weaken, chemical reactions slow, and the constant microscopic disturbances that dominate ordinary matter begin to fade. Cooling seems at first like a simple process. Place an object beside something colder, allow energy to leave, and its temperature falls. Continue long enough, and it might appear that the object should eventually become completely cold. Nature places a limit on that process. There is a lowest possible temperature, known as absolute zero. It is the point at which a system has the smallest amount of thermal energy allowed by the laws of physics. Nothing can be cooled below it, and no practical process can reach it exactly. Absolute zero corresponds to 0 Kelvin. On the Celsius scale, it is approximately 273 degrees below zero. The Kelvin scale begins at this physical limit, which makes it especially useful in science. A temperature of 1 Kelvin is 1 degree above absolute zero, while a temperature of 100 Kelvin is 100 degrees above it. It is tempting to imagine absolute zero as a state in which every atom becomes completely motionless. That picture is useful only as a rough introduction. Quantum mechanics does not allow particles in matter to become perfectly still in the ordinary sense. Even in their lowest possible energy state, particles retain a minimum amount of quantum activity. An atom confined within a solid cannot have both a perfectly fixed position and completely absent motion. The rules of quantum physics place a limit on how precisely those properties can be defined together. The atoms therefore retain what is often called zero-point motion. Cooling removes thermal excitations, but it does not turn matter into a collection of perfectly frozen particles. This difference matters because temperature is not a direct measurement of every kind of microscopic energy. A system can reach its lowest thermal state while still possessing quantum energy. Absolute zero means there is no lower thermal state available under the same conditions. It does not mean that all energy has vanished. The impossibility of reaching absolute zero is described by the third law of thermodynamics. One practical consequence of this law is that each step toward absolute zero becomes more difficult than the step before it. As the material grows colder, less thermal energy remains available to remove. Cooling methods become less effective, and unwanted energy from the environment becomes increasingly important. A warm object can lose energy quickly to a much colder environment because the temperature difference is large. Near absolute zero, finding an environment that is meaningfully colder becomes impossible. Scientists must use carefully designed processes that transfer small amounts of energy out of the sample while protecting it from every possible source of heating. Ordinary refrigeration cannot approach these temperatures. A household freezer may cool food to several tens of degrees below the freezing point of water, but that is still extremely warm compared with the lowest temperatures reached in laboratories. Even liquid nitrogen, which appears intensely cold in everyday demonstrations, remains many tens of Kelvin above absolute zero. Liquid helium allows scientists to move much lower. Helium remains liquid at temperatures where most substances are solid. Under ordinary pressure, it does not freeze merely through cooling. Its atoms are light, and their quantum motion is strong enough to prevent them from settling easily into a conventional solid structure. Pressure must be added if solid helium is required. When helium is cooled below a few Kelvin, it begins showing properties that have no ordinary room temperature equivalent. One form of liquid helium becomes a superfluid. It can flow with almost no ordinary viscosity, pass through extremely narrow openings, and move in ways that seem strange when compared with water or oil. The unusual behavior occurs because a large number of helium atoms enter a coordinated quantum state. Instead of behaving only as separate particles that happen to occupy the same container, they display collective behavior governed by one shared quantum description. This does not mean that every atom occupies exactly one location or follows one path. It means the usual individual particle picture becomes incomplete. The atoms act together on a scale large enough to produce visible effects. Very low temperatures allow this behavior to appear because thermal disturbances have been reduced. At higher temperatures, energetic collisions continually disrupt delicate quantum relationships. Cooling quiets those disturbances and allows collective patterns to survive. A similar principle appears in superconductivity. An ordinary metal resists electric current. Moving electrons interact with the atomic structure, transfer energy, and produce heating. In a superconducting material below a certain critical temperature, electrical resistance can fall to zero. The electrons form a coordinated state that moves through the material without the usual scattering process. A current placed in a closed superconducting loop can continue for an extremely long time, without an ordinary power source maintaining it. Superconductors also interact with magnetic fields in unusual ways. They can exclude magnetic fields from their interior or trap them in controlled patterns, depending on the material and conditions. This allows demonstrations in which a magnet appears to float above a cold superconducting surface. The effect is not simply caused by cold metal becoming a stronger ordinary magnet. It comes from the quantum behavior of the superconducting state. Heating the material above its critical temperature destroys that state, resistance returns, and the special magnetic behavior disappears. Different superconductors require different temperatures. Early examples worked only a few degrees above absolute zero. Later materials were discovered that become superconducting at temperatures high enough to be reached using liquid nitrogen. These are still very cold by everyday standards, but they are easier and less expensive to maintain. Cooling matter far below the temperature of liquid helium requires more specialized methods. One important approach begins with evaporative cooling. The principle is similar to the cooling produced by sweat. A trapped group of atoms contains a range of energies. Some atoms are more energetic than average. Scientists adjust the trap so that the most energetic atoms can escape. Those departing atoms carry away more than the average share of energy, leaving the remaining group colder. The process is repeated while the trap is gradually changed. Fewer atoms remain, but their average energy continues to fall. Evaporative cooling can produce extremely low temperatures when the atoms are first isolated and slowed using other methods. Before evaporation becomes effective, lasers are often used to cool gases of atoms. Laser cooling may sound contradictory, because light usually transfers energy into matter. Under carefully controlled conditions, light can slow atoms instead. Light carries momentum. When an atom absorbs a particle of light, its motion changes slightly. Scientists direct laser beams toward atoms from several directions and tune the light so that atoms moving toward a beam are more likely to absorb it. An atom traveling toward the incoming light receives a small push opposite its motion. It later releases light in a random direction. Across many absorption and emission events, the carefully directed slowing effects accumulate while the random effects tend to balance. The atoms lose organized kinetic energy and become colder. Several laser beams can create a region in which atoms are slowed from all directions. The result is sometimes described as optical molasses, because the atoms move as though they are passing through a thick fluid, although no actual molasses is involved, and the laboratory is usually cleaner. Magnetic fields can then trap suitable atoms so that they do not collide with the walls of a container. A collision with an ordinary solid surface would transfer far too much energy into such a cold sample. Atoms must be held away from warmer matter using fields or focused light. The entire experiment also needs an extremely good vacuum. Gas molecules from the surrounding air would strike the cold atoms and heat them. At room temperature, those unwanted molecules carry vastly more energy than the carefully cooled sample. Even a single collision can disturb the experiment. Vacuum chambers are therefore designed to remove nearly all background gas. Pumps, sealed materials, cleaned surfaces, and careful construction reduce the number of stray molecules. Radiation creates another problem. Every warm object emits infrared radiation. The walls of the room, the equipment, the scientists, and the electrical components all send energy into the surroundings. A sample close to absolute zero can absorb a tiny amount of that radiation and warm noticeably. Cold experiments use shielding, reflective surfaces, nested temperature stages, and carefully chosen materials to reduce this transfer. Wires and supports must be designed so that they do not conduct too much energy into the sample. Measurements must be made without disturbing the system more than necessary. A thermometer cannot simply be placed against the coldest matter in the usual way. Contact with an ordinary thermometer would heat the sample. Researchers instead infer temperature from properties such as the speed distribution of the atoms, the population of available energy states, or the response of the material to controlled signals. At extremely low temperatures, the ordinary idea of a mercury column or metal probe becomes useless. Measuring the temperature becomes part of the cooling challenge. Another powerful technique is magnetic cooling. Some atoms and atomic nuclei behave like tiny magnets. In a magnetic field, they can become more orderly, with many of their magnetic directions aligned. The process begins while the material is connected to a colder surrounding system. A magnetic field is applied, and energy associated with the changing alignment is allowed to leave. The material is then isolated, and the field is gradually reduced. As the magnetic order decreases, energy is taken from other microscopic motions within the material. The temperature falls. This method can cool certain substances to extremely low temperatures, especially when nuclear magnetic effects are used. Dilution refrigeration provides continuous cooling at temperatures far below 1 Kelvin. It uses two forms of liquid helium that behave differently when mixed at low temperatures. Helium atoms crossing from one liquid phase into another absorb energy, allowing heat to be removed from an experimental region. The system circulates the helium mixture through several stages. It is technically complex, but it has become an essential tool in research involving quantum computers, superconducting circuits, and low-temperature physics. Many modern quantum processors must be kept only a small fraction of a Kelvin above absolute zero. Their delicate quantum states are easily disturbed by thermal energy. Cooling reduces unwanted excitations and helps the devices behave in a controlled way. The refrigerator used for this purpose is not a larger version of a kitchen appliance. It is a carefully arranged structure of vacuum chambers, metal plates, shields, tubes, and cooling stages. The coldest components are isolated deep inside, while cables carry signals between the processor and warmer electronic equipment. Those cables create a difficult compromise. They must deliver information, but they can also conduct energy into the cold region. Engineers add filters, thermal connections, and attenuators at different stages to remove unwanted energy before it reaches the processor. Vibration can also produce heating. Machinery in the building, pumps, footsteps, and sound can cause small mechanical movements. At ordinary temperatures, these effects may be insignificant. Near absolute zero, even tiny disturbances can matter. Electrical noise has a similar effect. Unwanted signals can transfer energy into sensitive circuits. Experiments use shielding, grounding, filtering, and careful control of every connection. The coldest samples are therefore not simply placed in something cold, they are protected from the rest of the world. Cooling becomes an effort to prevent every known route by which energy can enter. Scientists have cooled gases of atoms to temperatures measured in billionths of a Kelvin and below. These temperatures are far colder than natural environments commonly found in space. Interstellar space is sparse, but it is filled with background radiation left from the early universe. That radiation has a temperature of a few Kelvin. A laboratory sample can be colder because it is shielded and actively cooled. The achievement applies to a very small amount of matter, often a thin cloud containing a limited number of atoms. It would not be possible to cool an entire room to the same temperature using existing methods. The amount of matter being cooled is important. Removing energy from a microscopic atomic cloud is difficult but manageable. Removing comparable energy from a large object would require vastly more equipment and protection. The coldest atomic gases can enter a state known as a Bose-Einstein condensate. This occurs for particles belonging to a particular quantum group. At very low temperatures, a large fraction of the particles occupy the lowest available quantum state. Their individual wave properties overlap, and the group behaves like a single matter wave. The condensate can display interference, flow, and other effects that reveal quantum mechanics on a scale much larger than one atom. Producing the condensate requires the atoms to be cooled and confined carefully. Laser cooling reduces their motion. Magnetic or optical traps hold them in place, and evaporative cooling removes the more energetic atoms. As the temperature falls, the quantum wavelengths associated with the atoms become longer. Eventually, those wavelengths overlap enough that treating the atoms as completely separate objects no longer works. A different group of particles, known as fermions, cannot all occupy the same quantum state. When fermionic atoms are cooled, they form another unusual type of matter known as a degenerate Fermi gas. Their behavior is controlled by the rules that also shape electrons in metals and matter inside dense stars. Low-temperature experiments allow scientists to study these systems under controlled conditions. By adjusting magnetic fields, density, and interactions, researchers can create models of materials that would otherwise be difficult to examine. Cold atoms can simulate magnetism, superconductivity, and other collective phenomena. They provide a way to test how complex behavior emerges from simple quantum rules. The lowest temperatures also change chemical reactions. At ordinary temperatures, atoms approach one another with a range of speeds and directions. At ultra-cold temperatures, their motion is so limited that quantum wave behavior dominates collisions. Reactions may slow, accelerate, or follow pathways that would normally be hidden. Researchers can sometimes control interactions using magnetic fields and prepare particles in specific quantum states. This makes ultra-cold matter useful for more than setting records. It allows precise measurements of time, gravity, fundamental constants, and tiny forces. Atomic clocks rely on carefully controlled atoms, and colder atoms can be observed for longer periods with less motion disturbing the measurement. Cold atom instruments can detect changes in acceleration and rotation. They may be used for navigation, underground mapping, tests of gravity, and searches for subtle physical effects. Cooling can also reduce noise in detectors. Thermal motion creates random disturbances in mechanical and electrical systems. Lowering temperature can make weak signals easier to identify, though quantum noise and other limits remain. Telescopes designed to observe faint infrared radiation are often cooled so that their own equipment does not produce overwhelming thermal radiation. A warm telescope glows in infrared wavelengths. Cooling the instruments makes the distant signal easier to separate from the heat of the detector itself. Some space telescopes use shields to block sunlight and allow their instruments to cool naturally. Others carry active cooling systems. The aim is not always to approach absolute zero, but to become cold enough that thermal emission from the instrument no longer hides the objects being studied. The approach toward absolute zero reveals a general pattern. As thermal motion decreases, ordinary behavior does not simply become slower and quieter. New forms of organization appear. Electrical resistance may vanish. Fluids may flow without ordinary friction. Atoms may behave as one shared quantum system. Magnetic properties may change. Heat capacity can fall sharply. The material begins responding according to rules that were always present but hidden by stronger thermal disturbances. Cooling, therefore, does more than remove energy. It changes which effects dominate. At room temperature, a delicate quantum relationship may survive for an unimaginably short time before collisions destroy it. Near absolute zero, the same relationship may remain long enough to measure and use. There is still no final step that reaches absolute zero. Suppose a cooling method reduces the temperature by removing the most energetic particles. As the sample becomes colder, fewer energetic particles remain to remove. The process becomes slower and less efficient. Suppose another method depends on transferring energy to a colder reservoir. As the sample approaches the reservoir temperature, the transfer weakens. To continue cooling, an even colder reservoir is needed. Every method faces a similar problem. The closer the system comes to its lowest thermal state, the harder it becomes to remove the remaining thermal energy. Reaching the exact limit would require an unlimited number of steps, perfect isolation, or an impossible process. Scientists can approach absolute zero as closely as their equipment and methods allow, but the remaining distance can always be divided again. A sample at 1/1000th of a Kelvin is extraordinarily cold, yet it is still above 0 Kelvin. The third law also suggests that the entropy of a perfectly ordered crystal approaches a minimum as temperature approaches absolute zero. Entropy concerns the number of microscopic arrangements available to a system. At high temperatures, many arrangements and excitations are accessible. Cooling restricts those possibilities. Real materials may contain defects, mixtures, or competing structures that prevent perfect order. Some retain residual disorder even at very low temperatures. The exact behavior depends on the system. Removing thermal energy does not necessarily create a simple, neat crystal. Quantum interactions can produce highly organized but unfamiliar states. In other cases, particles may become trapped in disordered arrangements because they cannot move enough to find a lower energy structure. Glass provides an ordinary example of matter becoming trapped outside a regular crystal arrangement. As certain liquids cool, their motion slows before the particles can organize into a crystal. The result is a rigid but disordered solid. At very low temperatures, similar questions become important in more strongly quantum systems. The lowest energy state may involve complicated patterns of magnetism, entanglement, or collective motion. The practical meaning of temperature can also become less clear when a system is not in equilibrium. A small group of particles may have different energy distributions in different directions. Electrons may be hotter than the atomic structure. One set of vibrations may be excited while another remains quiet. In those cases, researchers may assign different effective temperatures to different parts of the system, or avoid using one temperature until energy has been redistributed. Temperature remains powerful, but only when the system has enough internal balance for the concept to apply. There are even carefully prepared systems described using negative absolute temperatures. The name sounds as though they're colder than absolute zero, but they are not. They occur only in systems with an upper limit on available energy, and a specially inverted population of states. Such systems are actually hotter than any positive temperature because they tend to transfer energy to ordinary matter. They do not violate the lower limit of 0 Kelvin. The negative sign describes an unusual energy distribution rather than a temperature below the coldest possible state. This is another reminder that temperature is a statistical description. It reflects how particles occupy available energy states. Under ordinary conditions, higher energy states are less populated than lower ones. In an inverted system, more particles occupy the upper states, producing the negative temperature description. These unusual cases require careful preparation and do not occur in an ordinary glass of water or block of metal. They are useful because they test the deeper meaning of temperature beyond the familiar hot and cold scale. For everyday matter, the direction remains simple. Energy leaves a warmer object and enters a cooler one until equilibrium is approached. Cooling removes accessible thermal energy, reduces random microscopic activity, and reveals behavior that was hidden at higher temperatures. The closer matter comes to absolute zero, the less it resembles an ordinary collection of particles bouncing independently. Quantum effects spread across the system. The difference between one particle and the group becomes less clear, and the properties of the material depend on collective states. Extreme cold is therefore not an empty absence of activity. It is a carefully controlled condition in which thermal disturbance has been reduced enough for other forms of physical behavior to become visible. At the opposite end of our experience, the matter around us is rarely protected from energy so completely. It is warmed by sunlight, chemical reactions, electricity, friction, pressure, radiation, and contact with other matter. Planets form hot, stars produce energy, living cells release it, and the surrounding universe carries a long history of heating and cooling. The temperature of an object in front of us may have been shaped by events that began far away or long ago. The energy in a warm room may come from fuel formed from ancient organisms. The warmth of the ground may come from sunlight released by nuclear reactions in the sun. The heat inside the body may come from food that once captured that sunlight through plants. Following those connections takes temperature beyond the behavior of one cold sample or one hot surface. It leads into the history of matter itself, from the early universe and the first stars to planets, oceans, living cells, and the steady warmth maintained inside the human body. The warmth inside your body is connected to events that began long before Earth existed. The connection is not symbolic, it is a physical sequence of energy transfers involving expanding gas, gravity, nuclear reactions, sunlight, chemical bonds, food, oxygen, and the controlled reactions taking place inside living cells. To follow that sequence, begin with the early universe. Matter did not start in the form of cool rocks, oceans, plants, and people. The young universe was extremely hot and dense. Particles carried enormous amounts of energy and interacted constantly. Conditions were too energetic for ordinary atoms to remain intact. As the universe expanded, its energy became spread through a larger volume. The temperature fell. Particles that had moved too energetically to remain joined could begin forming more stable combinations. Atomic nuclei formed first. Much later, when conditions had cooled enough, electrons became bound to nuclei and produced neutral atoms. Most of the ordinary matter was hydrogen, with helium and small amounts of a few other light elements. The universe continued expanding and cooling, but matter was not distributed with perfect uniformity. Some regions contained slightly more material than others. Gravity strengthened those differences. Gas moved toward the denser regions. As a cloud contracted, particles accelerated inward. Their organized falling motion was converted into microscopic motion through collisions and compression. The central parts of the cloud became hotter. This is one of the main ways gravity creates heat. Gravity does not manufacture energy from nothing. Matter in a spread-out cloud has gravitational potential energy because it can fall inward. As the cloud collapses, that stored energy becomes motion. Collisions then distribute the motion among particles, raising the temperature. The contracting cloud can eventually form a young star. Before nuclear reactions begin, gravity provides much of the heating. The central gas becomes denser, pressure increases, and the particles move with greater energy. If the forming star contains enough mass, the central temperature and pressure become high enough for nuclear fusion. Atomic nuclei approach one another closely enough to undergo reactions despite their electrical repulsion. Hydrogen nuclei combine through a sequence of processes that eventually produce helium. The final products have slightly less mass than the original particles. The missing mass appears as released energy. That energy begins in the central region of the star. It is absorbed, scattered, and re-emitted many times as it moves outward. It also travels through the motion of hot plasma in regions where matter circulates. The energy does not pass directly from the center to the surface in one uninterrupted beam. Its journey can be extremely slow. Particles and radiation interact repeatedly before the energy reaches the outer layers and escapes into space. Once it leaves the star, some of the energy travels as visible light. Other portions travel as infrared radiation, ultraviolet radiation, and different wavelengths of electromagnetic radiation. A very small fraction reaches Earth. Most passes by the planet or strikes other objects. The portion intercepted by Earth becomes one of the main energy sources for the atmosphere: oceans, land, and living systems. Sunlight striking the top of the atmosphere can be reflected back into space, scattered or absorbed. Clouds reflect part of it. Air molecules absorb particular wavelengths. The surface receives what remains. Oceans, soil, plants, buildings, and skin absorb different amounts depending on their materials and conditions. Absorbed radiation transfers energy to electrons, atoms, and molecules. Their internal activity increases and the material warms. The ground does not keep all that energy. It transfers some into the air through contact. It releases infrared radiation. It warms water that later evaporates. Energy moves continuously between the surface, atmosphere, oceans, and space. Earth reaches a broad temperature balance because incoming energy is eventually matched by outgoing energy. The planet would continue warming if it absorbed energy faster than it released it. It would cool if it released more than it absorbed. The atmosphere influences this balance. Certain gases absorb part of the infrared radiation leaving the surface. They emit radiation in different directions, including back toward the ground. This slows the rate at which energy escapes to space and keeps the surface warmer than it would be without those gases. The basic greenhouse effect is a natural part of Earth climate. Changes in the concentration of greenhouse gases alter the balance and can change the average temperature over time. The surface is not warmed evenly. The equatorial regions receive more concentrated sunlight on average than the polar regions. Land and water respond differently. Day alternates with night. Seasons change the angle and duration of sunlight. These uneven temperatures create motion, Warm air expands, becomes less dense and rises. Cooler air moves in beneath it. Pressure differences drive winds. Ocean water circulates as temperature, salinity, and wind move energy around the planet. Weather is partly the result of the atmosphere trying to redistribute energy. Storms, clouds, winds, rain, and ocean currents move heat from one place to another. Water plays a major role because it can store large amounts of energy. Oceans warm slowly and cool slowly. Coastal regions often experience milder temperature changes than inland areas because nearby water absorbs and releases energy over long periods. Evaporation carries energy away from the surface. Water vapor can travel with moving air. When it condenses into cloud droplets, it releases energy into the atmosphere. A storm can therefore be powered partly by energy that was absorbed by ocean water and later moved through evaporation and condensation. Sunlight warms the ocean, water evaporates, vapor rises, condensation releases energy, and that energy strengthens atmospheric motion. Not all of Earth's warmth comes from the sun. The planet also contains internal energy. Some remains from its formation, when smaller bodies collided and combined under gravity. Large impacts converted motion into heat. Compression increased internal energy. Dense materials moved toward the center, releasing gravitational energy as Earth separated into layers. Radioactive elements within the planet continue to decay and release energy. Particles and radiation from those decays interact with surrounding matter, increasing microscopic motion. This internal energy drives processes beneath the surface. Hot material moves slowly within the mantle. Magma rises in some regions. Volcanoes release hot rock, gas, and ash. Warm water circulates through cracks and can return to the surface in hot springs. The center of Earth remains extremely hot, but that does not mean the surface is heated mainly from below. Sunlight dominates most surface temperature patterns. Internal energy is more important for geology, volcanic activity, and the long-term behavior of the planet. The matter that formed Earth also contained elements produced in earlier generations of stars. The first stars were made mostly from hydrogen and helium. Nuclear reactions inside them created heavier elements. Some massive stars produced elements through several stages of fusion. Explosions and stellar outflows scattered those elements into space. Later clouds formed new stars, planets, and smaller bodies from the enriched material. The carbon in living tissue, the oxygen in the blood, the calcium in bones, and the iron used to carry oxygen were formed through processes involving stars. Some were produced inside stars during their lives. Others were created or dispersed during violent stellar events. Those atoms eventually became part of the cloud that formed the sun and its planets. On Earth, they entered rocks, oceans, the atmosphere, and living organisms. The energy inside your body today is not the same energy that once heated the early universe, but its sources belong to the same continuing physical history. Matter and energy have been changing form and moving between systems for billions of years. Plants provide one of the clearest links between sunlight and biological warmth. During photosynthesis, plants absorb light using specialized molecules. The energy supports chemical reactions that build energy, rich organic compounds from simpler materials. Sunlight does not remain trapped inside a leaf as light. Its energy becomes part of chemical arrangements. The plant uses some of that energy for growth, maintenance, reproduction, and transport. Animals obtain chemical energy by eating plants, or by eating other organisms that ultimately depend on plants. Fungi and many microorganisms also obtain energy from chemical substances in their surroundings. When food enters your body, digestion breaks large molecules into smaller ones. Carbohydrates can be broken into simple sugars. Fats are separated into smaller components. Proteins are broken into amino acids. These substances enter the blood and are transported to cells. Inside cells, controlled reactions release usable energy from them. Oxygen taken in through the lungs plays a central role in much of this process. It enters the blood, binds to molecules in red blood cells, and is carried through the body. Cells use oxygen in reactions that transfer energy from food molecules. The process occurs through many carefully regulated steps. Releasing the energy all at once would be damaging and difficult to control. Some of the energy is captured in molecules that cells can use for immediate work. These molecules power muscle contraction, active transport across cell membranes, construction of new cellular material, and many other processes. A significant portion becomes thermal energy. Collisions, molecular rearrangements, friction within tissues, and the general inefficiency of biological processes distribute energy into microscopic motion. This heat is not merely waste, it helps maintain the temperature required for human biology. Enzymes, membranes, nerves, and muscles work best within a limited temperature range. The body constantly balances energy production against energy loss. Even while resting, organs remain active. The heart contracts, the diaphragm moves, the brain processes signals, cells repair damage, and chemical reactions maintain electrical and chemical differences across membranes. This resting activity produces heat. Physical exercise increases energy use, so heat production rises. Muscles convert chemical energy into movement, but only part becomes useful mechanical work. Much of the remainder becomes thermal energy. Run, cycle, lift a heavy object, or climb stairs, and the body warms. Blood carries energy away from active muscles and distributes it through the body. Temperature sensors in the skin and inside the body send information to the brain. A region in the brain helps coordinate responses that keep the internal temperature within a safe range. When the body becomes too warm, blood vessels near the skin widen. More warm blood reaches the surface. Energy then moves into the environment through radiation, conduction, convection, and evaporation. Sweat glands release water onto the skin. If the water evaporates, energetic molecules leave the liquid and carry energy away. The remaining skin becomes cooler. Sweating works best when the air is dry and moving. High humidity slows evaporation because the air already contains a large amount of water vapor. Sweat may remain on the skin without providing enough cooling. When the environment is hotter than the skin, the body may gain energy from the surroundings. Evaporation becomes especially important because radiation and convection may no longer remove enough heat. If the body cannot release energy as fast as it produces or absorbs it, internal temperature rises. Proteins can lose their proper shapes, membranes can be disrupted, and the nervous system can begin to fail. When the body becomes cold, it responds differently. Blood vessels near the skin narrow, reducing energy transfer from warm blood to the environment. The hands, feet, ears, and nose may cool first as the body protects the temperature of central organs. Muscles may begin shivering. Rapid contractions use chemical energy and increase heat production. The movement is not intended to carry the body anywhere. Its main result is increased internal energy. Hormones can alter metabolism, changing the rate at which cells use stored chemical energy. The body may also encourage behaviors such as seeking shelter, adding clothing, curling up, or holding a warm drink. Clothing helps by slowing energy transfer. A coat traps air, and still air conducts thermal energy poorly. Several thin layers can trap more air than one compressed layer. Blankets work in the same way. They do not provide a continuing supply of heat by themselves. They reduce the rate at which the body loses the heat produced by metabolism. Food provides the chemical energy needed to replace what the body uses. A person living in a cold environment may require more energy, if the body must continually produce extra heat. The energy in food can often be traced back to sunlight. A piece of bread contains energy stored in molecules made from plants. Fruit was built by a plant using absorbed light. Meat contains energy obtained from an animal that ate plants or other animals. A meal may therefore become body heat through a long sequence. Nuclear fusion releases energy in the sun. Radiation travels to Earth. A plant absorbs part of it and stores some in chemical bonds. Food carries those molecules into the body. Cells release the energy through controlled reactions. Some becomes movement, while some becomes thermal energy. The sequence is not perfectly efficient. Energy spreads at every stage. The sun sends radiation in all directions, and Earth intercepts only a small part. Plants store only part of the light they receive. Digestion and metabolism lose energy as heat. Muscles produce heat while doing work. This spreading is not an error in the system. It is a basic feature of energy transfer. Useful concentrated energy tends to become more widely distributed. A warm body releases energy into the room. The room releases energy through walls, windows, and ventilation. The building releases radiation into the surroundings. Earth eventually emits energy into space. The energy is conserved through these changes, but its ability to perform useful work becomes reduced as it spreads. A hot object and a cold object can drive change while their temperatures differ. Once both reach the same temperature, the shared thermal energy is still present, but it is less available for producing organised motion. Living organisms maintain their internal organisation by taking in concentrated energy and releasing more dispersed energy and matter. Food and oxygen enter. Heat, carbon dioxide, water and other products leave. Life does not violate the general tendency for energy to spread. It creates local organisation by using energy and increasing the overall dispersal in the environment. The warmth you feel in your hand is therefore the visible result of many invisible processes. Blood carries energy from active tissues. Chemical reactions continue inside cells. Molecules collide and vibrate. Infrared radiation leaves the skin. Air molecules strike the surface and carry energy away. Touch another person, and energy moves between both surfaces according to their temperatures. A warm hand can transfer energy into a colder hand. After contact continues, the temperatures near the touching surfaces approach one another. The feeling of warmth also depends on nerves and blood flow. A hand that has been outside in winter may interpret ordinary indoor objects as warm. A hand that has been close to a heater may find the same objects cool. A thermometer provides a more objective reading, but even it must exchange energy with the body before measuring. It reaches a condition close to thermal equilibrium and uses a calibrated physical response to report the temperature. The body is not at one perfectly uniform temperature. The internal organs are usually warmer and more stable than the skin. Fingers and toes can vary significantly. Recently active muscles may be warmer than resting tissues. Blood, breathing, and conduction move energy between regions. The body continually adjusts rather than holding every cell at one exact value. Temperature also varies within cells. Microscopic processes can briefly release energy in particular locations. At such small scales, assigning an exact local temperature can become difficult, because equilibrium may not exist over such a tiny region. For ordinary medical purposes, broader measurements are sufficient. They indicate whether the body is maintaining its normal range or responding to infection, inflammation, exposure, or other stress. Fever is a regulated rise in the body's temperature setting. Signals associated with the immune response cause the control system to defend a higher temperature. A person may feel cold and begin shivering, even while the measured temperature is rising. The body behaves as though it is below its new target and tries to produce and conserve heat. Later, when the target returns toward normal, the person may feel hot and begin sweating. The body now tries to lose the additional energy. The value of fever depends on its cause, intensity, and duration. A moderate rise can affect biological processes and immune activity, while excessive temperature can become dangerous. The internal warmth of mammals and birds allows many body systems to operate with less dependence on outdoor temperature. Maintaining that warmth requires continuous energy. Reptiles and many other animals rely more directly on external energy. They move between sunlight and shade, warm surfaces and cool shelters, using behavior to regulate body temperature. A lizard resting on a sunlit rock absorbs radiation. Its body warms, chemical reactions speed, and muscles become more effective. When it grows too warm, it moves into shade or a burrow. The energy source differs from the constant internal production emphasized in mammals, but the physical process remains the transfer and distribution of energy among particles. Plants also have temperatures and thermal limits. Leaves absorb sunlight, exchange energy with air, release water vapor, and emit infrared radiation. Their temperatures can differ from the surrounding air. Evaporation through small openings in leaves provides cooling. Leaf shape, color, orientation, and surface structure influence how energy is absorbed and released. Some flowers and plant structures can produce additional heat through rapid metabolism. This warmth may help spread scents or attract pollinating insects. Microorganisms generate heat as they process nutrients. A compost pile can become noticeably warm because bacteria and fungi release energy through chemical reactions. A large, well-supplied pile can reach temperatures high enough to change which organisms survive inside it. Stored plant material can also heat through biological and chemical activity. If energy cannot escape quickly enough, the temperature may rise substantially. Under some conditions, this can create a fire risk. Matter does not need to be alive to carry the same history of energy transfer. A brick wall warms in sunlight and cools after sunset. A parked car absorbs radiation, traps warm air, and reaches a higher internal temperature. A lake stores summer energy and releases it during autumn. Everything around you is participating in exchanges of thermal energy. The rate may be fast or slow, obvious or difficult to measure. No ordinary object is completely isolated. Even space is not entirely empty or perfectly cold. Radiation travels through it. Thin gas contains moving particles. Dust grains absorb starlight and emit infrared radiation. A planet without a nearby star can still contain internal heat from formation, gravity, radioactive decay, or tidal forces. Gravitational interaction with another body can bend and deform the planet repeatedly, converting mechanical energy into thermal energy. Moons orbiting giant planets can experience strong tidal heating. Their interiors are stretched as the gravitational force changes across their orbits. Friction within the material produces heat, which can drive volcanic activity or maintain liquid water beneath an icy surface. Temperature can therefore reveal hidden energy sources. A world that emits more energy than it receives from sunlight must have another source. A cloud of gas glowing in space may be heated by nearby stars, shocks, magnetic fields, or energetic particles. Astronomers learn about distant temperatures by studying radiation. The wavelengths and intensities of emitted light provide information about the energy distribution in stars, gas, dust, and planets. No thermometer has been placed inside the Sun or against a distant galaxy. Temperature is inferred from the behavior of radiation and matter. The same physical principles connect those remote measurements to a thermometer beneath the tongue. Both depend on how energy is distributed among particles and how that distribution affects measurable properties. The scale changes enormously, but the meaning remains related. In a star, temperature describes a plasma of nuclei and electrons. In the body, it describes water, proteins, salts, fats, gases, and living cells. In the air, it describes moving molecules. In a solid thermometer, it changes electrical resistance or another physical property. Matter gets its temperature from its energy history. It may have absorbed sunlight, undergone compression, reacted chemically, carried electrical current, fallen through gravity, collided with another object, or received energy from warmer surroundings. Its present temperature shows the balance reached after those processes have added, removed, and redistributed energy. A hot drink remembers the kettle only through its current microscopic state. The water molecules do not carry a label identifying the power station that supplied the electricity. The energy has already been shared through collisions, rotations, vibrations, and molecular interactions. As the drink cools, that energy moves into the mug, table, air, and surrounding surfaces. Some leaves as infrared radiation, Some causes air to circulate. Some helps water molecules evaporate. Eventually the drink approaches the temperature of the room. The energy has not disappeared. It has become more widely distributed. The same thing happens to the heat produced by your body. It moves into clothing, bedding, furniture, air, and nearby walls. The room eventually releases it into the wider environment. A small part may travel outward as radiation and continue through the atmosphere. Earth itself releases energy into space, maintaining the broad balance that allows surface temperatures to remain within a range where liquid water and life can exist. The path from cosmic events to body warmth is therefore continuous. Gravity gathered gas into stars, nuclear fusion released energy, radiation crossed space, Earth absorbed part of it, plants stored part of that energy chemically. Food carried it into living bodies, cells released it again. Microscopic motion increased and skin became warm. Other roots join the same system. Earth's internal energy warms parts of the crust. Human technology converts chemical, nuclear, mechanical, and electrical energy into heat. Weather moves energy through water and air. Life captures, stores, uses, and releases it. Temperature is the measurement that allows us to describe the result without tracking every atom and every transfer. It tells us whether energy is likely to move into or out of another object. It helps determine whether water freezes, metal melts, air rises, proteins function, stars ignite, and planets maintain oceans. It is not a substance hidden inside matter. It is not the same as the total amount of energy. It is not measured perfectly by touch, and it is not always explained by particles simply moving faster through space. It is a collective property of matter connected to the way energy is distributed among movement, vibration, rotation, interactions, and quantum states. That answer began with ordinary warmth and led through atoms, solids, liquids, gases, plasma, extreme cold, stars, planets, and living cells. The route was long because temperature belongs to nearly every physical process around us. Look at any object near you, and its temperature has a history. A window may be losing energy to the night air. A phone may be warming as electrical energy moves through its circuits. A blanket may be slowing the loss of heat from your body. A glass of water may be approaching the temperature of the room. Your own warmth is being produced and regulated at this moment. Food molecules are being processed. Oxygen is being transported. Blood is moving. Cells are releasing energy. The surrounding air is carrying some of that energy away. The process continues whether you pay attention to it or not. There is no need to feel the atoms moving or to notice every transfer. A comfortable room, a steady breath, and the warmth beneath a blanket are enough evidence that the exchange is taking place. If this journey has helped make the subject clearer, or simply provided a calm place to rest for a while, you can like the video and subscribe to Physics with William. It helps more listeners find these slow explanations of the physical world. Wherever you are listening from, the matter around you is still exchanging energy. The air is moving, surfaces are emitting radiation. Your body is balancing the heat it produces with the heat it releases. The temperature beside you may be ordinary, but the process behind it reaches from the smallest collisions inside matter to nuclear reactions inside stars. There is no separate supply of hotness placed into the universe. There is energy moving, changing form, and becoming distributed among particles. That is where matter gets its temperature from. For now, allow the room to remain at whatever temperature it has reached. Let the blanket keep doing its quiet work. Let the air move without needing to follow every molecule. Sleep well, wherever you are, and take care until the next slow journey through physics.